Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Let me know quickly in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Quickly in the chats. Welcome back, welcome back, welcome back. Welcome back, my dear students. Welcome back. Perfect. So people, I hope all of you know that today we are starting the NEET 2025 Endgame series on this particular channel, right? We are going to do every chapter of your physics, chemistry, as well as the biology, right? We are going to cover them in a single session. And every session exactly is going to be for 3 to 4 hours. Okay? Well, I know it's going to be really difficult to complete the whole chapter in 3 to 4 hours. So I might be a little fast, but I want you guys to coop up the speed with me. Okay? And that's the only thing. I would say that's the only way by means of which we can complete the entire syllabus through this Endgame 2025 series as well. All those students who are yet to start their preparation, all those students who have not completed their 100% of the syllabus, who have just completed a certain percentage of the syllabus, my dear students, this particular series is for all of you. Okay? Perfect. So today, our chapter is going to be, as you all must be knowing, our chapter is going to be atomic structure. Okay? The next chapter which I will be doing, that is going to be the general organic chemistry. I'll be starting with the high weightage chapters first. Okay, today we shall be doing the atomic structure. My next session, that is going to be on Friday, and that's going to be your general organic chemistry. Perfect. Similarly, your Yavar sir, he is going to start with gravitation tomorrow, right? Similarly, your Ambika ma'am, right? She is also going to start from those chapters which were not completed in the bounce back series. Perfect. But that does not mean we are going to only complete certain chapters. We'll be completing all the chapters here in this particular series. It is just, we want you guys to follow this particular series throughout these like 60, 70 days. Perfect. So that you can score well when it comes to your NEET 2025 examination. So are you all ready? Let me know in the chats. Yes, today is the first class. Are you all ready? Let me know quickly in the chats. Yes, even JEE aspirants can also watch it. JEE aspirants can also watch it. My dear students, the duration of the session is going to be 3 to 4 hours. And I would want you guys to be with me till the end. Because I'm not going to give any sort of break in between. Because if I keep on giving breaks in between, then the session duration is going to exceed for sure. Which is something I do not want at all. Okay? Perfect. So today, it's going to be the atomic structure. The next chapter which I'll be doing on Friday, that's going to be your general organic chemistry. Everything will be covered. Everything will be covered. Don't worry about that. We know how to complete the chapter in 3-4 hours as well. Okay? We have already covered chapters in like 10-12 hours. Perfect. That was one series, your game of NEET. Now, let's complete the chapters in 3-4 hours as well. But one thing, again, I'm repeating the same thing. I would want you guys to be with me till the end. If you are ready to do that, let me know once in the chats quick. That is going to be boosting up my confidence level as well. Yeah? Perfect. Amazing. And my dear students, at the same time, one more thing. The PDF of this particular session. The PDF of this particular session I'll be sharing on my Telegram channel. And I'm pretty much sure all of you are already the part of my Telegram channel. And if you are not, join in quickly. It is Wassim Bhat Chemistry Official. That is the name of the Telegram channel in which I shall be sharing the handwritten PPT of this particular chapter. Handwritten PDF of this particular chapter. All right. One more thing before starting. One more thing. My dear students, since we are going to complete each and every chapter in 3 to 4 hours. So at some times, we shall be going into the depth wherever I Wherever I think that I need to teach the concept in depth, I'll be doing that. Wherever I feel there is no need to go into the depth, it's better to remember things, there you will have to remember things, right? That's how we are going to crack this particular examination with a good score. Perfect? Perfect. And please, all the spammers can go home, right? You have got a lot of channels on YouTube. Perfect. If you want to spam, you can go there. So let's get going then. Let's get started with the chapter Atomic Structure. Well, first of all, this is going to be the table of content. These are basically the topics of atomic structure from which questions will be asked. I'm not going to teach you any irrelevant stuff. I'm not going to teach you that stuff which is not asked. Perfect. I will be focusing on that stuff from which questions will be asked. These are the topics, my dear students, in the chapter Atomic Structure from which questions will be asked. Apart from these topics, questions won't be asked in your NEET 2025 examination when it comes to the chapter Atomic Structure. Okay? So the first topic with which we shall be starting the session, that is going to be your Planck's quantum theory. Okay? That is going to be your Planck's quantum theory. So let's get going. Let's get started with the Planck's quantum theory. And the ones who have not subscribed to this particular channel yet, I would want you guys to subscribe to the channel right now so that you remain updated about all the sessions which we are going to take on this particular channel in this NEET Endgame series. Okay? Perfect. So my dear students, Planck's quantum theory. What Planck's quantum theory exactly says? What this theory exactly is all about? My dear students, I have mentioned three important points over here. I've mentioned three important points over here. The first point, if you look carefully, according to this theory, energy is transmitted. According to this theory, energy is transmitted in the form of small packets. In the form of small packets. Or I can say in the form of small units. And those packets, those units are what you call as quanta. Those packets, those units are what you call as quanta. What exactly that means? For example, over here you have got a source of energy. Let's say this is the source of energy, which is continuously emitting the radiations. Let's say over here you have got a source of energy. Source of energy, which is continuously emitting the radiations. My dear students, let's say this is the radiation which I'm focusing upon. This is the radiation which this energy source is emitting. As per your Planck's quantum theory is concerned, this radiation over here, it consists of small packets. It consists of small packets, right? And these small packets of which radiation consists of, these small packets of which radiations consist of, these small packets, if I talk about this particular packet, if I talk about this particular unit, you call this as the quantum. You call this as the quantum. And a lot of these units are what you call as quanta. A lot of these units are what you call as quanta. Now, my dear students, let's say this source of energy, it is emitting light radiation. If this source of energy is emitting light radiation, in case of light radiation, this quantum is what you call as photon. In case of light radiation, this quantum is what you call as photon, right? So if you have got the source of energy, it is going to continuously emit the energy. Perfect. So the radiation which the source of energy is emitting, it consists of small discrete packets. Perfect. Those packets are what you call as quantum, right? And a lot of these packets are called as quanta. In case of the light radiation, this quantum is what you call as photon. This is point number one. This is point number one. So in case of light radiation, in case of light energy, these packets are what you call as photons. And my dear students, in vacuum, photon travels with the speed of light. In vacuum, this photon, it travels with the speed of light. And you know that already, 3 into 10 raised power 8 meter per second. Perfect. Now, my dear students, let me tell you a few important things. First of all, energy carried by a photon. Energy carried by a photon. Energy carried by a single photon. Energy carried by a single photon, which I'm representing with E. Remember the formula? E is equal to h nu. E is equal to h nu. Energy carried by one photon, which I'm representing with E, that's equal to h nu. This is the first result. Number two, you can write the same result in a different format as well. You can write E is equal to h. What is nu? Nu is the frequency of the light. And you know, frequency nu is nothing but C divided by lambda. You can write it in this format as well. E is equal to hc divided by lambda. Energy carried by one photon is equal to h nu, or you can say hc divided by lambda. Okay. Now, my dear students, if I ask you, energy carried by one photon is equal to h nu. What about energy carried by two photons? That will be 2 times h nu. Energy carried by 3 photons, that will be 3 times h nu. So, my dear students, if I make a general result, energy carried by n number of photons, energy carried by n photons, what do you think that will be? Energy carried by n photons, what do you think that will be? I would say energy carried by n photons, that I'm representing with E, is going to be equal to n times h nu, number 1, or it's going to be n times hc divided by lambda. Perfect. N times h nu, or you can say it's going to be n times hc divided by lambda. Am I clear with this? Am I clear with this? Yes or no in the chats? My dear students, one more thing. One more thing. What is that exactly? First of all, if I talk about the units of energy, that is important. If I talk about the units of energy. So you tell me in the chats, what is the SI unit of energy? What is the SI unit of energy? SI unit of energy is what? That is your joule. Now, in this particular chapter, we are not going to take only SI unit into consideration. There is one more important unit of energy which I will take into consideration here. There is one more important unit of energy. What is that unit of energy? That's what you call as electron volt. That's what you call as electron volt. This is one more unit of energy which I'll be using here. Okay, electron volt. And remember, 1 electron volt is nothing but, it is 1.6 into 10 raised power minus 19 joules. 1 electron volt is nothing but 1.6 into 10 raised power minus 19 joules. Okay? Right? These are all the very, very, very important points which I'm giving you. And I'll be using them directly in the questions in some time. One more thing which I would want to tell you over here. What is that exactly? My dear students, try to understand what exactly I'm going to say. Just a second. Yeah. One more thing which I would want to say over here. Which color should I use? Which color should be visible here? I think this is the only one. Okay. Do you see h over here? Planck's constant. Do you see c over here? Speed of light. H is a constant which has got some value. You know, 6.6 into 10 raised power. The value of h. The ones who do not know, 6.6 into 10 raised power minus 34 joule second. Perfect. C, the speed of light, 3 into 10 raised power 8 meter per second. So h is a constant, c is a constant. My dear students, remember one simple thing. H multiplied by c. H multiplied by c. Remember one unique value of h multiplied by c. H multiplied by c, you'll be taking as 12400 electron volt angstroms if lambda is taken in angstroms. H multiplied by C is nothing but 12400 electron volt angstroms when lambda is taken in angstroms. Okay? And my dear students, remember one more thing. H multiplied by C, you can take as 1240 electron volt nanometer when lambda is taken in nanometers. When lambda is taken in nanometers. Remember these 2 points as well, because I'll be frequently using these two terms. H multiplied by C is 12400 electron volt angstroms, and H multiplied by C is equal to 1240 electron volt nanometer when lambda is taken in nanometers. I believe every single thing in this particular slide is absolutely clear to every one of you. Okay? Yes or no in the chats quick? Yes or no in the chats quick? And if it is a yes, then let's try to solve this question. If it is a yes, then let's try to solve this particular question, which is on your screen. The question says, calculate the energy of 100 photons. Calculate the energy carried by 100 photons. So n is equal to 100. If the wavelength of the light is 2000 angstroms, we need to calculate energy carried by 100 photons, my dear students. You already know the formula. E is equal to NHC divided by lambda. Perfect. What is the value of n? That's 100. Since lambda I'm taking in angstroms, my dear students, if lambda is taken in angstroms, then H multiplied by C will be taken as 12400 electron volt angstroms divided by, what is my lambda? My lambda is 2000 angstroms, right? So this angstrom cancels out, right? This 000, this 00 and 0 cancels out. So what do we get over here? I'll be getting something as 1240 divided by 2 electron volts, right? Which comes out to be 620 electron volts. So energy carried by 100 photons over here is going to be 620 electron volts. Perfect. Now, if they ask you the same thing in joules, since you have calculated the energy in electron volts and you already know how to convert this into joules, it's pretty much simple. It's going to be 620 multiplied by 1 electron volt is nothing but 1.6 into 10 raised power minus 19. Then the answer is going to be in joules as well. I believe this particular stuff is clear to everyone. I believe this particular stuff is clear to everyone. If yes, let me know quickly in the chats. Everybody. Quickly. Yeah? Amazing. Amazing, guys. Look at one more question then. Look at one more question, people. The question says a light source, a source of light of wavelength 2000 angstroms emits energy which is 0.5 joules. The number of photons emitted from the source. The number of photons emitted from the source. So in this particular question, you're again supposed to get the value of n. So which result you guys are going to use? Which result you guys are going to use? Check it out. You know, E is equal to NHC divided by lambda. Okay. My dear students, energy on the left hand side is given in terms of joules. So your left hand side is given in terms of joules. Okay. People, if left hand side is given in terms of joules, then your right hand side should be again as per SI system as well. Left hand side, I'm writing as per SI system. So right hand side should be also written in terms of SI system as well. Right? If left hand side is written in terms of SI system, so your right hand side should be written in terms of SI system as well. So what I'll be writing? Since n value I need to calculate, H value as per SI system is 6.6 into 10 raised power minus 34 joule second. C value as per SI system 3 into 10 raised power 8 meter per second divided by lambda. Also I have to write as per SI system, and as per SI system is the unit angstrom or meter. As per SI system, the unit has to be meter. So I'll be writing 2000 into 10 raised power minus 10 meters. Perfect. Right, people? Now, over here, it is just the matter of calculation, as you can see. It is just the matter of calculation. Perfect. So, you just got one equation which just has one variable, and over here, you can easily get the value of n. I believe this is also clear to everyone. I believe this is also clear to everyone. If I'm clear to everyone, I want some fire emojis in the chats quickly. Everybody. Everybody in the chats. This was 2000 angstroms. But angstrom is not the unit as per SI system. As per SI system, meter is the unit. So I converted angstroms into meters. And you must be knowing 1 angstrom is equal to 10 raised power minus 10 meters. Okay? Perfect. Perfect, perfect, perfect. Amazing, guys. Now there is one more terminology over here, which is what you call as power. Which is what you call as power. My dear students, how do we define the term power? How do we define the term power, which I'm representing with P? Power is simply defined as energy emitted from the source divided by the time taken. Energy emitted divided by time taken. Energy emitted from the source divided by time taken is what you call as power. So in short, you can write it as E divided by T. My dear students, let's say this is energy emitted from the source. Let's assume that source is emitting n photons. Let's assume that source is emitting n photons. If source is emitting n photons, what about the energy emitted by n photons? It's going to be n times h nu divided by t. Or you can write it as n times hc divided by lambda. And in the denominator, you have got t as well. Perfect. Right? I believe this is clear to everyone. So, my dear students, power of the source. Power of the source is nothing but energy emitted by the source divided by time taken. So, I'm assuming that source is emitting n photons. Energy carried by n photons is nothing but nhc divided by lambda, right? And in the denominator, you have got time. Perfect. So what did we get? We got n divided by t multiplied by hc divided by lambda. This is the result which I would want you guys to remember. People, do you see this particular term n by t? Do you see this particular term n by t? This n by t combinedly is called as the rate of emission of photons. This n by t combinedly is what you call as rate of emission of photons. Or you can say number of photons per unit time. Number of photons per unit time or rate of emission of photons. One more thing. I believe all of you would be knowing what is the SI unit of power. SI unit of power. In the charts quickly. SI unit of power in the charts quickly. Quickly in the charts. Everybody. Everybody. Absolutely. It's watt. Perfect. Perfect, guys. From this particular result, again, question can be asked. And what can be the question? Question is going to be in this format. Question is going to be in this format. Guys, I want you to be active in the chats throughout the session. That's how it's going to be fun teaching as well as learning. Right? I want you guys to be active in the chats. All right, this is the question. How many photons are emitted per second? Look at the question carefully. How many photons are emitted per second? So what are we supposed to calculate? Think over it. What are we supposed to calculate? How many photons are emitted per second? We are supposed to calculate n by t. Number of photons emitted per second, which is what you call as the rate of emission of photons. So I need to get the value of n by t. How many photons are emitted per second by a 5 milliwatt laser? So you have got a source of energy, that is a laser. right? You are given with the power of laser, that is 5 milliwatt, which can be written as 5 into 10 raised power minus 3 watts. Okay, operating at 620 nanometers. Operating at 620 nanometers. Perfect. So tell me the result which I'll be using here. Everybody, tell me the result which I'll be using here. Few minutes back, I gave you result. P is equal to N divided by T, HC divided by lambda. Perfect. What am I supposed to calculate? I want this particular term. So N divided by T is nothing but P multiplied by lambda divided by H multiplied by C. This is something which I need. This is something which I need. In this particular equation, use all the terminologies as per your SI system, because power I've converted as per SI system. So lambda has to be in terms of SI system as well. 620 nanometers. 1 nanometer is 10 raised power minus 9 meters. So it is 10 raised power minus 9 meters. This is your lambda. So it's going to be P is equal to 5 into 10 raised power minus 3. Your lambda is equal to 620 multiplied by 10 raised power minus 9. H value as per SI system is 6.6 into 10 raised power minus 34. And C, your speed of light, that is 3 into 10 raised power 8. This is just the matter of calculation. You can easily solve and kill this particular question. Well, do not expect this sort of calculation in your NEET exam. Calculation part is going to be easy. It is just you have to understand the concept. Calculation part in the question is going to be easy in your NEET exam. That's something which I'm telling you again and again, right? Okay. It is just, you just need to know the concept. Don't worry about the calculation. Calculation part is going to be easy in the exam. Perfect. Amazing. My dear students, our next topic is something which all of you love, because this is something which you study in your physics as well, and that too in a very detailed manner. Okay? That too in the very detailed manner. So let's try to understand this particular topic. The topic is your photoelectric effect. People, what is your photoelectric effect? How do we exactly define it? What kind of questions can be asked? Let's try to understand. Let's try to understand. See guys, let's try to understand. First of all, this photoelectric effect, it supports which nature of light? Does it support particle nature of light? Does it support the wave nature of light? Remember, my dear students, this photoelectric effect, it is going to support the particle nature of light. Point number one. Point number two. Let's read this paragraph once and then I'll make you understand what exactly it means. See guys, as per this photoelectric effect is concerned, when light is incident on a certain matter, when light is incident on a certain matter, electrons are emitted. Electrons are emitted from the surface of the matter. When light is incident on the metal, electrons are emitted from the metal. These electrons which are emitted, these electrons which are ejected from the metal, these are what you call as photoelectrons. These are what you call as photoelectrons. The current that flows due to the motion of these photoelectrons, the current that flows due to the motion of these photoelectrons is what you call as photocurrent. Is what you call as photocurrent. And this overall phenomenon is what you call as photoelectric effect. Now try to understand what it means. Try to understand what it means. Try to understand what it means. My dear students, imagine that this is your metal surface over here. This is your metal surface. Perfect. Now people, you must be knowing in the metal surface, you will be having the positively charged ions as well as the electrons. There would be positively charged ions as well as electrons present here. Absolutely. There would be positively charged ions as well as the electrons present here. Now, my dear students, can I say these electrons, they are held by these positively charged ions? Absolutely. Positive, negative, there will be attraction. There will be attraction. So these electrons, they'll be held by the positively charged ions. Perfect. So electrons here are bounded. It's a bounded system. Electrons are bounded here. It's a bounded system. Now, my dear students, since electrons are bounded, if you want to take this electron out, what do you have to do? I'll say you have to break all the attractions. You have to break all the attractions between the electron and the nucleus. I mean, between the electron and these ions. Since this particular electron, which I'm mentioning over here, this particular electron is bounded. This particular electron is being attracted by these positively charged ions. So if you want to take this electron out, you have to break the force of attraction between the ion and the electron. And in order to break the force of attraction, what do we need? We need to supply energy. And the energy which I'm supplying, that's what I'm supplying in the form of light. Perfect. So light is being incident on the metal surface. It's breaking down all the attractions between the electron and the ions, right? And eventually the electron is coming out. Perfect. And the electron that comes out of the metal surface is what you call as photoelectron. And the current that gets generated due to the motion of these photoelectrons is what you call as photocurrent. I believe this is clear to everyone. Right? And this overall phenomenon is what you call as photoelectric effect. Right? Sir, your Telegram channel name. Telegram channel name is Wassim Bhat Chemistry Official. WASSIM BHAT Chemistry Official. That is the Telegram channel name. So I hope you got the insights of what this photoelectric effect is all about. Now, people, let's try to understand a few more things. Let me tell you, the minimum energy required by the electron to come out, the minimum energy required by the electron, or you can say the minimum energy required to eject the electron out of the surface of the metal. That's something which you call as work function, which is represented by phi. The minimum energy which is required to eject the electron from the surface. The minimum energy which is required to eject the electron from the metal is what you call as work function. Perfect. And my dear students, this work function, it's a characteristic of a metal. So every metal has got a particular value of work function. Let's say work function of metal X is 3 electron volts. That means minimum 3 electron volts is to be supplied to eject the electron. Let's say work function of some metal Y is 5 electron volts. That means minimum 5 electron volts is to be supplied to knock out that electron. So work function is a characteristic of a metal. It is different for different metals. Okay? The minimum energy which is required to eject the electron from the metal is what you call as work function. And my dear students, the minimum frequency of the incident light, which is required, to eject the electron is something which you call as the threshold frequency, which I'm representing with nu naught. So 2 terms. One is your work function, or you call that as threshold energy as well. Okay? One is your work function, one is going to be your threshold frequency. Work function is the minimum energy required to eject the electron. Threshold frequency is the minimum frequency of the incident light required to eject the electron. Okay? Perfect. So, if I talk about this work function, which I'm representing with phi, or you can represent it with phi naught. Remember, it is equal to h nu naught. Remember, my dear students, this phi is equal to h nu naught. What is phi naught? It is the work function. What is nu naught? It is the threshold frequency of the incident light. Perfect? Right? Now, my dear students, what is nu? Nu is equal to c divided by lambda. Nu is equal to C divided by lambda. Can I write nu naught would be equal to C divided by lambda naught? So one more term came into existence. What is that? That is threshold wavelength. Threshold wavelength. What was nu naught? It was minimum frequency of the incident light. It was minimum frequency of the incident light. It was minimum frequency of the incident light to eject the electron. So what would be threshold wavelength? If this is minimum, then this has to be maximum. This is going to be the maximum wavelength of the incident light to eject the electron. Maximum wavelength required to eject the electron out of the surface of the metal is what you call as threshold wavelength. So first term was your work function. Second is your threshold frequency. Third is your threshold wavelength. Perfect. And my dear students, phi or phi naught is nothing but h nu naught, or you can say it is equal to hc divided by lambda naught. Perfect. Is this particular point clear? Quickly in the chats. Is this particular point clear? Quickly in the chats. Well, I've already made the slides. Otherwise, I used to use the blank slides. But if I use the blank slides, it's going to take a lot of time. So I've already designed the slides earlier so that it's going to save our time. Okay? Perfect, people till here? In the chats quickly, everybody. Everybody in the chats. Everybody in the chats. Now, this is something important. This is something important. My dear students, this is your metal surface. This is your metal surface. And these are the positively charged ions. These are the positively charged ions, and in between we have got electrons. In between we have got electrons. In between we have got, for example, electrons. These electrons are bound. They are being attracted by this positively charged ion, this positively charged ion, this one as well, right? So there is force of attraction between electron and the ions. There is force of attraction between electron and the ions. Okay. Now, in order to take this electron out, as I told you already, in order to take this particular electron out, what do I need to do? I need to break this attraction. I need to break this attraction. How can I break the attraction? I can break the attraction if I supply some energy in the form of light. If I supply some energy in the form of light. Let's say the energy carried by this light radiation, E, right? E is equal to h nu. Energy carried by this light radiation, that's E, which is equal to h nu. Perfect. Now, my dear students, imagine that the minimum energy required to take the electron out is, for example, 60 joules. Just to make you understand. Let's say minimum energy required to take this electron out is 60 joules. For example, from here, I'm supplying some 100 joules. From here, I'm supplying some 100 joules. I'm supplying some 100 joules. But minimum, how much is required to take the electron out? 60 joules. So first of all, this 100 particular joules which I'm supplying, out of these 100 joules, 60 joules would be used to break the attractions, and the remaining 40 joules would be given to the electron. Remaining 40 joules would be given to the electron to provide maximum kinetic energy for this particular electron. So basically, the energy which you are supplying, it is divided into two parts. Some part of energy is used to take the electron out, and the remaining part is taken by the electron in the form of its maximum kinetic energy. Perfect. That's what is written here. The energy incident on the metal surface is used in two parts. Number one, to eject the electrons out of the surface of the metal in the form of work function, to provide the kinetic energy to the ejected electron. So can I say your incident energy, it is divided into two parts. Some part of it is used for the work function, and the remaining part is given to the electron in the form of its maximum kinetic energy. Perfect. So this is one equation which is very important. From this equation, question can be asked, right? Now, this is one of the format of the equation. The second format of the equation, incident energy is equal to h nu, work function is equal to h nu naught plus Ke max. plus Ke max. This is one more format of this equation. This is one more format of this particular equation. Or you can write it like this. E H nu. Instead of nu, I can write C by lambda. H nu naught. Instead of nu naught, I can write C divided by lambda naught. Plus what? Plus your kinetic energy max. Plus your kinetic energy max. This is one more format of this equation. This is one more format of this equation. I'm giving you one more format. What is that? If you look at this particular equation, if you look at this, or let's have a look on this particular equation. H nu is equal to H nu naught plus, instead of maximum kinetic energy, I'm going to write E V naught. What is V naught here? V naught denotes the stopping potential. I believe you would have studied it somewhere in your physics. V naught is your stopping potential, and this nu naught is your threshold frequency. It is your threshold frequency. Am I clear with this? Am I clear with this, people? These are the 4 equations which I would want you guys to remember. And I hope you got to know how we got these equations. I hope you got to know how we got these equations. Yeah? Am I clear? Let me know once in the chats quick. Let me know once in the chats quick. Everybody. 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 Let me know once in the chats. All right. My dear students, I'm going to plot a graph. I am going to plot a graph. The graph is between kinetic energy and the frequency of the incident light. Kinetic energy and the frequency of the incident light. I need to plot this graph. How this graph will look like. See guys, have a look on this particular equation, which we already derived. Can I write this equation in a different format? I can write your kinetic energy max is equal to, this is your H nu minus H nu naught. Correct? Now, if you see carefully, kinetic energy I'm plotting along y-axis. Okay? This nu I'm plotting along x-axis. This becomes your m. And this entire term becomes your c. The sign is minus. Y is equal to mx minus c. Y is equal to mx minus c. It is going to be a straight line first of all. It is going to be a straight line. The intercept is negative. Intercept is negative, right? And the slope is positive. Perfect. So it's going to be a straight line with the negative intercept. Let's say this was the origin. It's going to be a straight line like this. Okay. Perfect. The distance from the origin to the point from where the graph starts. The distance from the origin to the point from where the graph starts is called as intercept, c. And c over here is nothing but h nu naught. Slope is represented by m, and m over here is equal to h. So slope of this particular graph is nothing but h. Okay? All right, people? Am I clear with this? Am I clear with this? My dear students, there is one more thing which you need to know. What is that? See, photoelectric effect, this is also called as, it is also called as one photon, one electron emission. This is also called as one photon, one electron emission. What does that mean? That means one photon can take out only one electron. One photon can take out only one electron. One photon can never take out 2 electrons. Okay? One photon can take out only 1 electron. What does that mean? What does that mean? For example, this is the surface of the metal. Perfect? Let's say this is the electron which I'm considering. I have to take this electron out. Let's say minimum 50 joules of energy is required to take the electron out, which is its work function. Perfect? Let's say I've got one photon over here, which is going to be incident on this electron. Let's say this photon carries the energy of 100 joules. Let's say this photon carries the energy of 100 joules. Now, don't think like this 100 joules will break into 2 parts, 50 and 50. 150 joule would be required to take this electron out. One more 50 joule would be required to take one more electron out. That's not the case. We call this as one photon, one electron emission. One photon can take out only one electron. So if this photon carries 100 joules, out of 100 joules, 50 joules is required to take the electron out. And the remaining 50 joules will be imparted to the electron in the form of its kinetic energy. Got it? Is this particular point clear? So for each incident photon, only one photoelectron is emitted. Point number one, given in your NCERT. Second one, there is no time lag. There is no time lag between striking of the photon and emission of photoelectron. What does that mean? That means as soon as the photon hits the electron, at that point itself, the electron comes out. There is no time lag. There is no time lag. It's not like the photon has struck the electron and after 5 seconds, 10 seconds, electron will come out. No, the process is all spontaneous. The process is all instant. As soon as the photon hits the electron, at the same time, this electron comes out of the surface. There is no time lag at all. This is one more important point which I wanted to share with you. Now, my dear students, one more thing. If you ask me, what is the condition for the photoelectric effect to happen? What is the condition? What is the condition for the photoelectric effect to happen? The condition is pretty much simple. Incident energy should be greater or equal to the work function. If the incident energy is greater or equal to the work function, then only electron can come out. Then only electron can come out. Okay? Then only electron can come out. I can write it like this. Incident energy is equal to h nu. Phi naught can be written as h nu naught. So h gets cancelled. So nu has to be greater or equal to nu naught. This becomes my one more condition. This was first condition. This becomes my second condition. What is nu? It is the frequency of the incident light. The frequency of the incident light should be greater or equal to threshold frequency. Okay? Frequency of the incident light should be greater or equal to threshold frequency. Now, one more thing. What is nu? C divided by lambda. What is nu naught? C divided by lambda naught. C gets cancelled. So what do I get? 1 by lambda should be greater or equal to 1 divided by lambda naught. If I take the reciprocal, I'll say lambda should be less or equal to lambda naught. This is one more condition in terms of wavelength. This is one more condition in terms of wavelength. So, energy of the incident light should be greater or equal to work function. Okay. The frequency of the incident light should be greater or equal to threshold frequency. The wavelength of the incident light should be less or equal to the threshold wavelength. Okay. Right, people? So, remember, if these conditions are fulfilled, then only your photoelectric effect is going to happen. If I'm clear, let me know once in the chats. Quickly. Perfect? Perfect, guys? If this is perfect, then this is the question for you. This question will make sure that the concept is clear. The question says, if the work function of the metal, is equal to 3.1 electron volt, find its threshold wavelength. This is the first question. If the work function of the metal is 3.1 electron volts, find its threshold wavelength. You know, phi naught is equal to hc divided by lambda naught. As per the question, it's 3.1 electron volt. I can say lambda naught is equal to hc divided by 3.1 electron volt. Since the denominator is in electron volts, so numerator should also be in electron volts. What is the value of hc which I'll be using? 12400 electron volt angstrom. Should I take angstrom or nanometer? In the question, they have mentioned nanometer somewhere. So let's take everything in nanometers. So 1240 electron volt nanometer divided by 3.1 electron volts. Electron volt cancels out. So how much this comes out to be, lambda naught? Can you quickly let me know in the chats? 1240 divided by 3.1. How much it comes out to be? How much it comes out to be? Quickly in the chats. Everybody. Everybody. It approximately comes out to be? I need the approximate answer. Guys, you have to be fast. You're supposed to be fast. So it is coming out to be 413, right? So it's going to be 413 nanometers. So one question is solved. Lambda naught you have calculated. Second question. Find its threshold wavelength and find the maximum kinetic energy. Find the maximum kinetic energy of the electron emitted when the radiation of 300 nanometers strike the metal. So a radiation of 300 nanometers is striking the metal. So how much is the incident energy? Incident energy is equal to E is equal to hc divided by lambda. hc I'll be taking as 1240 electron volt nanometer. The wavelength of the incident light is equal to 300 nanometers. So how much is going to be your incident energy here? How much is going to be your incident energy here? Quickly. How much is going to be your incident energy here? Quickly in the chats. Quickly in the chats. How much is going to be your incident energy here? Approximately 4 point something. So incident energy is equal to approximately 4.1 electron volts. Approximately 4.1 electron volts. This is your incident energy. Now, my dear students, what am I supposed to calculate? Kinetic energy max. I already gave you an equation. Incident energy is equal to work function plus kinetic energy max. Okay. So I can say your kinetic energy max has to be equal to incident energy minus the work function. What is your incident energy? Incident energy is equal to 4.1 electron volt minus, what is my work function? My work function is 3.1 electron volt. So 4.1 minus 3.1 comes out to be 1 electron volt. So this is going to be your maximum kinetic energy which the electron has. Am I clear with this? Am I clear with this? Everybody in the chats? Am I clear with this? Everybody in the chats? Am I clear with this? Everybody in the chats? Who is the Shukla? Shukla, I'm sorry, you're blocked. Perfect, guys. Let's move on to one more question. Can you give this question a try? Can you give this question a try? The work function of some metals is listed below. These are the work functions of some metals. Lithium 2.4 electron volts. So minimum 2.4 electron volts is required to take the electron out from lithium. 2.3, 2.2. Okay. The number of metals which will show photoelectric effect when light of 300 nanometer falls on the metal. So light of 300 nanometers, we are going to fall on lithium, it will fall on sodium, it will fall on potassium, etc., etc. I need to check how many metals are there which will show photoelectric effect. Now, first of all, what is my incident energy? What is my incident energy? That's equal to hc divided by lambda. hc is equal to 1240 electron volt nanometer. What is my lambda here? Lambda is equal to 300 nanometer. So nanometer cancels out. How much this value comes out to be? Approximately 4.1 electron volts. This is my incident energy. What is the condition for the photoelectric effect to happen? I told you already, incident energy should be greater or equal to work function. This is the condition. Let's see where all this condition is being satisfied. Incident energy is equal to 4.1. Work function is equal to 2.4. So incident energy is greater than work function. Photoelectric effect will happen. Will happen. Will happen. Will happen. Here it won't happen. Here it won't happen. Here it won't happen. So there are technically 1, 2, 3, 4. There are 4 metals which are going to show the photoelectric effect right now. Am I clear, people? Am I clear, people? Everybody in the chats? Everybody in the chats, am I clear? Everybody in the chats quickly. Perfect. Now, my dear students, let's enter into one more topic. What is that? That's your Bohr's atomic model, right? From this particular topic, frequently you guys get the questions. Bohr's atomic model. So what this Bohr's atomic model is all about? My dear students, the first and the most important thing, the Bohr's atomic model is only applicable to the single electron species. To the single electron species, those species which just contain one electron. For example, you have got hydrogen. Hydrogen contains just one electron. You have got He positive, just contains one electron. Li di positive, just contains one electron. Be tri positive, just contains one electron. So first of all, remember the Bohr's atomic theory, the Bohr's atomic model is applicable only to the single electron species. Point number one. Point number two, which all of you would be already knowing. As per your Bohr's atomic model is concerned, electrons are revolving around the nucleus. Electrons are revolving around the nucleus. In the circular paths, electrons are revolving around the nucleus in the circular paths of constant radius, of fixed radius, of constant radius, of fixed radius. Okay, electrons revolve around the nucleus in the circular paths. Those circular paths have got fixed radius, and those circular paths are something which you call as orbits or shells. So electrons, they revolve around the nucleus, right? They revolve around the nucleus in circular paths. Okay, and those circular paths which have got fixed radius, right? Those circular paths are what you call as shells or orbits. It's not orbital I'm mentioning orbit. Next point. My dear students, it's pretty much evident for any object to move in the circular path, for any object to show the circular motion, the object should continuously experience centripetal force, by means of which the object will revolve in the circular path. Right? Right, people? For any object to show the circular motion, the object should continuously experience the centripetal force, which will make the object to move in the circular path. As per your Bohr's atomic model is concerned, say, let's say this is your atom. This is your atom, right? Its atomic number is Z. Atomic number is Z. If atomic number is Z, that means in the atom, there will be how many protons? In the atom, there will be how many protons? There will be Z number of protons. Okay? There will be Z number of protons. My dear students, if the atomic number of the atom is Z, that means there are Z number of protons. Let the charge carried by one proton is E. Let the charge carried by one proton is E. Therefore, charge carried by Z protons is Ze. And the sign is plus. Why? Because proton carries the positive charge. Who is this spamming nonsense? So what I'm trying to say is, the atom, its atomic number is Z, so there are Z protons. I would say charge carried by these Z protons is Ze, and this Ze charge is concentrated in the nucleus. So in the nucleus, you have got the positive charge. How much positive charge? Ze. Okay, perfect. My dear students, this is the electron which carries the negative charge. For this electron to show the circular motion, this electron should experience centripetal force. Centripetal force is nothing but mv square by r. Right? And let me tell you, as per Bohr's theory, the necessary centripetal force for the electron to move in the circular path is provided by what? Is provided by the electrostatic force of attraction. Is provided by what? Electrostatic force of attraction between the nucleus and the electron. Since there will be attraction between nucleus and the electron. Perfect. Nucleus carries positive charge. Electron carries negative charge. There is electrostatic force of attraction between them. So I would say the necessary centripetal force required for the electron to move in the circular path is provided by what? The electrostatic force of attraction. Electrostatic force of attraction is providing the necessary centripetal force. And I would simply say it like this: centripetal force is provided by the electrostatic force of attraction. I mean, electrostatic force of attraction is the cause, right, for the electron to move in the circular motion. Now, you know, centripetal force is equal to mv square by r. Electrostatic force is nothing but k q1 q2 divided by r square, right? So it's finally going to be mv square divided by r is equal to k. q1, charge in the nucleus, that is Ze. q2, charge on the electron, that's E. So it becomes Ze square divided by r square. So this is the equation which we got over here. One important equation. One important equation, people. Am I clear? Am I clear? Am I clear? Quickly in the charts. Now there is one more important thing. You need to remember this as well. My dear students, let's say this is your nucleus. This is shell number 1, this is shell number 2, shell number 3, shell number 4, shell number 5. This is shell number 1, this is 2, this is 3, this is 4, this is 5. Now, first of all, out of the infinite orbits, electron can only be present in that orbit. Electron can only be present in that orbit in which the angular momentum, which is mvr, angular momentum, is an integral multiple of h upon 2 pi. Since we have got electron is revolving around the nucleus. This is the electron. It has got mass. Electron is revolving, it has got velocity. You have got radius over here as well. So m multiplied by v multiplied by r is something which you call as angular momentum. So this electron over here has got the angular momentum. Now electron can be only present in that orbit in which the angular momentum is the integral multiple of h upon 2 pi. What does that mean? See guys, try to understand. If I put the value of n as 1 here, if I put the value of n as 1, that means I'm talking about the first shell. I am talking about the first shell. What is the angular momentum of electron in the first shell? It would be equal to h upon 2 pi. In the second shell, put n is equal to 2h upon 2 pi. 2 cancels out. So this is h upon pi. Put the value of n as 3. So this becomes 3h upon 2 pi. Similarly, 4h upon 2 pi. 5h upon 2 pi. Right? Now, first of all, in between 1 and 2, in between first shell and second shell, there'll be again some infinite number of shells. There will be a shell, right, whose shell number, for example, just to make you understand, would be 1.1, right? If you put ns, let's say that 1.1 shell number is this. Perfect. So what would be the angular momentum for this particular shell? It would be 1.1. It would be 1.1 h upon 2 pi. There'll be one more shell whose shell number is, for example, 1.2. For that, it will be 1.2 h upon 2 pi. Bohr series says that electron would only be present in that orbit. Electron would only be present in that shell in which the angular momentum would be the integral multiple of h upon 2 pi. That means electron will be either present in shell number 1, or it will be present in shell number 2, or it will be present in shell number 3, shell number 4, shell number 5. In between, there are infinite shells. Electron cannot be present in those shells. I believe I'm clear to everyone. I believe I'm clear to everyone. Yes? And this is something which you call as quantization of angular momentum. One more important thing. Remember this particular statement as well. The statement is, the electron while revolving around the nucleus, neither it gains energy nor it loses energy. Remember this particular point as well. The electron when revolving in an orbit, it neither loses energy nor it gains energy. And therefore, when the electron neither loses energy nor gains energy, electron will be continuously revolving in its orbit only. That's why we call these orbits as the stationary orbits. That's why these orbits are called as stationary orbits. Perfect. This was one more postulate which you need to know. Again, few more. By the way, this is something which you have to remember. And I believe this is something which you would have studied long back too. My dear students, look at the next statement. Next statement says that when the electron moves from lower energy shell to higher energy shell. When the electron moves from lower energy state to higher energy state, energy is absorbed by the electron. When the electron makes a transition from lower energy state to higher energy state, energy is absorbed by the electron. For example, this is shell number 1, this is shell number 2, this is shell number 3. Let's say electron has to go from 1 to 3. Electron is making a transition from lower energy state to higher energy state. Whenever electron makes a transition from lower to higher, energy is absorbed by the electron. And how much energy is absorbed by the electron? Whatever would be the energy gap between the two shells. Whatever would be the energy gap between these two shells. Same amount of energy the electron has to absorb. Then only it will go from shell number 1 to shell number 3. Okay? And similarly, when the electron makes a transition from higher energy state to lower energy state, higher to lower, it emits energy. It emits the same amount of energy which it had absorbed earlier. Am I clear with this? Am I clear with this? Yeah? So remember, when the electron makes a transition from lower to higher, it absorbs energy. When the electron makes a transition from higher energy state to lower energy state, it emits energy. Okay? It emits energy. And energy absorbed or emitted will be always the energy gap between the two shells. Energy gap between the two shells. Now, my dear students, comes certain points. First of all, this Bohr's model, it has got some applications as well. Okay? First of all, how do we calculate the radius of the Bohr's orbits? For example, this is the nucleus. This is the nucleus of an atom whose atomic number is, for example, Z. This is the nucleus of an atom whose atomic number is Z. Let's say electron is revolving in this shell. Let's say electron is revolving in this shell. I'm calling this shell as nth shell. I'm calling this shell as nth shell. How do we calculate the radius of this nth shell? How do I calculate the radius of this nth shell? Which is what you call as nth orbit as well. There is one result which I would want you guys to remember. Radius of nth Bohr's orbit, which we represent with Rn. Radius of nth Bohr's orbit is always equal to R naught n square divided by Z. It has got the derivation as well, but that derivation is of no use to you. Radius of nth Bohr's orbit is equal to R naught n square divided by Z. N represents the orbit number, shell number in which electron is present, right? And this Z represents the atomic number. Z represents the atomic number. Now, my dear students, you can do one more thing. First of all, this R naught. R naught is a constant here whose value is 0.529 angstroms. R naught is a constant here whose value is 0.529 angstroms. Now, imagine this is one of the atom whose atomic number is, for example, Z1, and the shell number in which electron is present is N1. Let's say I've got one more atom. Let's say I've got one more atom over here, right? Whose atomic number is Z2. Whose atomic number is Z2. Electron is revolving in this shell number, which I'm calling as N2. Electron is revolving in this particular shell, which I call as N2. I need to get this particular radius. Let's say if this radius was, for example, R1, let me call this radius as R2. How do I compare these two radiuses? How do I compare these two radiuses? These two radii I'll be comparing with the help of this result. I can say simply R1 divided by R2 is equal to N1 square divided by N2 square multiplied by Z2 divided by Z1. This is how you are going to compare these two Bohr's radiuses. Am I clear? Am I clear, people? Am I clear? Let me know once in the chats. Everybody? Everybody? Yeah? So this was the first case, radius of the nth Bohr's orbit. Second is velocity of the electron in the nth Bohr's orbit. Velocity of the electron in the nth Bohr's orbit. Velocity of the electron in the nth Bohr's orbit, which I represent with Vn. How do we calculate velocity of the electron in the nth Bohr's orbit? There is again one result which I would want you guys to remember. Velocity of the electron in the nth Bohr's orbit is equal to V naught Z divided by N. Z is the atomic number. N is the orbit number in which electron is revolving. Okay? And this V naught is equal to 2.18 into 10 raised power 6 meter per second. It's a constant. Similarly, if I want to compare the velocities of two electrons, I'll be using this result. V1 divided by V2 is equal to V1 divided by V2 is equal to Z1 divided by Z2 multiplied by N2 divided by N1. This is going to be my result to compare the velocities of two electrons moving in two different Bohr's orbits of two different atoms. Okay, this is one more important result. The third result is related to time period. Time period. How do we calculate the time period of electron? What is time period first of all? Time period is nothing but it is defined as time taken by the electron to complete one revolution. Time taken to complete one revolution. I'm giving you its formula directly. Time period of the electron in the nth Bohr's orbit. It is equal to T naught n cube upon z square. T naught n cube upon z square, where T naught is 1.6 into 10 raised power minus 16 seconds. Okay, n cube upon z square. If you want to compare the time periods of two electrons, which are moving in two different shells of two different atoms, how do we do that? It's going to be T1 divided by T2 is equal to, this is going to be N1 cube divided by N2 cube multiplied by Z2 square divided by Z1 square. Okay, this is how you calculate, right? This is how you calculate the time periods. Perfect. Similarly comes one more point. What is that? That is the frequency of the electron. Frequency of the electron in the nth Bohr's orbit. Frequency of the electron in the nth Bohr's orbit. Frequency of the electron in the nth Bohr's orbit. You know what is frequency? Frequency is basically inverse of time period. V nth would be equal to 1 divided by T nth. Right? Frequency is inverse of time period. Perfect. If time period was directly proportional to n cube, inversely proportional to z square. Therefore, frequency would be directly proportional to z square, inversely proportional to n cube. Simple. And here, my dear students, you can write like this. If you want to compare the frequencies of two electrons, this is going to be z1 square, this is going to be z2 square, this is going to be n2 cube, this is going to be n1 cube. Am I clear with all this? Say yes or no in the chats. Everybody. Am I clear with this? Am I clear with this? Everybody in the chats. Am I clear with this? Yeah? Okay? Perfectly done till here? Amazing, guys. If this is clear, tell me the answer of this question. If it's clear, tell me the answer of this particular question. Calculate the radius ratio of second orbit of He positive and third orbit of Be tri positive. So you have got two single electron species, He positive and you have got Be tri positive. Let me represent this as this with 1. Let me represent this with 2. I'm representing them with 1 and 2. Now, second orbit of He positive. Second orbit. So N1 is 2. Second orbit of He positive. What is the atomic number of helium? Hydrogen, helium. That's 2. Third orbit of Be tri positive. N2 is equal to 3. hydrogen, helium, lithium, beryllium. Atomic number is 4. Perfect. I gave you the result already. R1 divided by R2 is equal to n square by z. So it's n1 square divided by n2 square. This is z2 divided by z1. The radius ratio is going to be n1 ka square means 2 ka square 4 divided by n2 ka square 3 ka square 9. Z2 is 4. Z1 is 2, right? So it's going to be 16 divided by 9 2s are 18. So 2 8 2 9. So 8 is to 9 is the radius ratio which I was supposed to calculate. I believe this is clear. I believe this is clear. I believe this is clear. Yes? All right. What do you think about this particular question? What do you think about this particular question? What do you think about this particular question? If the velocity of the electron, if the velocity of an electron in the first orbit of hydrogen, so my first atom is hydrogen and my second atom is Li di positive, representing this with 1, representing this with 2. Now, if the velocity of the electron in the first orbit of hydrogen, is what? Is v. Velocity of the electron in the first orbit of hydrogen is v. Okay. What will be the velocity of the electron in the third orbit of Li di positive, hydrogen, helium, lithium, right? In the third orbit of Z2 is also 3. Atomic number of lithium is 3, right? And I need to calculate V2. Already I've given you one result. V is equal to V naught Z by N. V naught Z by N. So V1 divided by V2 is equal to Z1 divided by Z2. And this is going to be N2 divided by N1. Perfect. Now, my dear students, what is V1? V1 is V. V2 I need to calculate. What is Z1? Z1 is 1. What is Z2? Z2 is 3. What is N2? N2 is 3. And what is N1? N1 is 1. So this gets cancelled out. So from this particular equation, I got to know V2 is also equal to V. Perfect. I believe these sort of questions you can solve easily. Yes, I believe these sort of questions you can solve easily if you just remember the formulas. That's all. Perfect. One homework question. This is the similar question related to time period. Do give it a try on your own. I am moving on. My dear students, till now we discussed about radius, we discussed about velocity, we discussed about time period, we discussed about frequency. Now there are a few more things. What is that? First of all, total energy of the electron in the nth orbit. Total energy of the electron in the nth Bohr's orbit is what? It is the sum of kinetic energy possessed by the electron and the potential energy possessed by the electron. Total energy possessed by the electron is nothing but it is the sum of kinetic and potential energy possessed by the electron. Now, there are some derivations with the help of which we calculate total energy, kinetic energy, potential energy of the electron. But you have got nothing to do with the derivations. The results are important. And what are the results? Let me give them to you. Let me first of all tell you, kinetic energy possessed by the electron in the nth Bohr's orbit. Let's say this is the nucleus. The electron is revolving in this particular nth Bohr's orbit. Let's say atomic number of this particular atom is Z. Okay. So kinetic energy possessed by the electron in the nth Bohr's orbit is equal to 13.6 Z square divided by N square electron volts. The first result. Second, potential energy possessed by the electron in the nth Bohr's orbit is equal to minus 27.2 Z square divided by N square electron volts. Total energy, which I'm representing with E1, En. Total energy, which is sum of kinetic and potential, this plus this, it will be minus 13.6 Z square divided by N square electron volts. This is how you calculate total energy possessed by the electron in the nth Bohr's orbit. So these are the three results which you are going to remember. These are the three results, my dear students, which you are going to remember. One result is your kinetic energy of the electron in the nth Bohr's orbit. Second is potential energy possessed by the electron in the nth Bohr's orbit. The third one is the total energy possessed by the electron in the nth Bohr's orbit. This is the total energy possessed by the electron. Now, people, just try to understand few things. Just try to understand few things. This result is giving me the total energy possessed by the electron. The total energy possessed by the electron. Now, understand one thing. Understand one thing. Understand one thing. Understand one thing, guys. If you increase the value of n, if you increase the value of n, that means you are going far from the nucleus. If you increase the value of n, that means you are going far from the nucleus. If you increase the value of n, this E should decrease. This E should decrease, correct? But there is a minus sign. So technically what I'm trying to say is, on increasing the value of n, the value of 13.6 z square by n square, the value of this particular term, 13.6 z square by n square, it should decrease. On increasing the n, you are increasing the denominator. So this whole term will decrease. If this whole term is decreasing, then minus 13.6 z square by n square. This term is decreasing. If this term is decreasing, with the minus, the term will increase. And if this whole term is increasing, what does that mean? That means energy is increasing. So what can we conclude from here? What can we conclude from here? As we move far from the nucleus, energy of the electron increases. So this is one important statement which you guys are going to remember, right? I mentioned it over here. As the value of n increases, the total energy of the electron also increases. As the value of n increases, the total energy possessed by the electron also increases. Perfect? Perfect, guys? Am I clear with this? Am I clear with this quickly in the chats? Everybody? Quickly in the chats, everybody? So people, let's have a look on something very important. Let's have a look on something very important. Very, very, very important. Since I'm talking about the hydrogen atom, I am talking about the hydrogen atom. Okay? I am talking about the hydrogen atom. For example, how do we calculate energy of the electron in the nth Bohr's orbit? It's minus 13.6 z square divided by n square. For hydrogen atom, z value is already 1. For hydrogen, z is already 1. If the electron is present in the first shell of hydrogen, that means n is also 1. Z is 1, n is also 1. So what would be the energy carried by the electron in the first shell of hydrogen? It's going to be minus 13.6 electron volts. This represents your n is equal to 1 of hydrogen. If the electron is present in n is equal to 1 of hydrogen, energy carried by the electron will be minus 13.6 electron volts. If the same electron goes to shell number 2, put the value of n as 2 here. Z is already 1. Put the value of n as 2. 2 ka square is 4. 13.6 divided by 4 comes out to be 3.4. So minus 3.4. This is the energy carried by the electron when present in the second shell of hydrogen. Similarly, energy carried by the electron in the third shell of hydrogen. Energy carried by the electron in the fourth shell of hydrogen. Okay? Perfect. Let me first of all tell you, n is equal to 1. This is what you call as ground state. This is what you call as ground state. N is equal to 2 is what you call as first excited state. Ground state, first excited state. N is equal to 3 is what you call as second excited state. N is equal to 4, you'll be calling as third excited state. You'll be calling as third excited state. My dear students, tell me one thing. What is the energy gap between first and the second shell? Energy gap between first and second shell. How do we calculate this energy gap? Delta E. Energy gap between second and first would be equal to final minus initial. So minus 3.4 minus initial is minus 13.6. When you solve it, the value comes out to be 10.2. So energy gap between first and the second shell is 10.2 electron volts. Energy gap between 2 and 3 is 1.89 electron volts. So if you think logically, energy gap between first and second shell is 10.2. Second and third, it is equal to 1.89. So as we move far from the nucleus, right, the energy gap between the consecutive shells, that keeps on decreasing. Remember this particular point. As the number of shells increase, the energy gap between the two successive shells will keep on increasing. So energy gap between 1 and 2 is more. Energy gap between 2 and 3 will be comparatively less. Energy gap between 3 and 4 will be lesser. Energy gap between 4 and 5 will be less. Okay? Remember this particular point. This is important. As we move far from the nucleus, energy gap between the two consecutive shells, that will keep on decreasing. Okay? Now, my dear students, one more thing. See, do you see energy of the electron in the first shell is minus 13.6, negative. Minus 3.4 in the second shell, negative. Minus 1.5, negative. Minus 0.85, negative. So what does this negative sign indicate here? This negative sign indicates that electron is under the influence of the nucleus. This negative sign indicates that electron is under the influence of nucleus. That means minus 13.6. It means that nucleus in the first shell, when the electron is in first shell, nucleus will be holding the electron. When the electron is in second shell, nucleus will be still holding the electron. When the electron is in third shell, nucleus will be still holding the electron. When the electron goes to infinite shell, E infinity is 0. It means that now the electron is out of the influence of the nucleus. Now nucleus is not holding the electron. Perfect? Now nucleus is not holding the electron. So basically, if you need to take out the electron from the atom, if you need to take the electron out from the atom, if you want to take the electron out from the atom, that means you have to send the electron to infinity. You have to send the electron to this particular energy state. Because when the electron reaches this energy state, infinite energy state, it automatically means electron is now not under the influence of the nucleus. Am I clear, everybody? Let me know once in the chats quick. Did you understand all this properly? Did you understand all this properly, people? Everybody? Everybody in the chats? Everybody in the chats? Everybody in the chats? Quick, quick, quick. Quick. Yeah? Perfect. Look at this particular question. Guys, there is no break. Even I have not had my dinner. I'll have it once the session ends. And it's been only 1.5 hours. We have been studying. So we need to wait for like 2 more hours. In 2 more hours, the chapter will be completed. Don't worry. Okay? After that, you guys can have dinner. I can have my dinner too. All right. Look at this particular question. Radiation corresponding to the transition n is equal to 2 to n is equal to 4 to n is equal to 2 in hydrogen falls on the metal of work function 2.5 electron volts. The maximum kinetic energy of the photoelectron in joules would be. Okay. So first of all, let's say this is your n is equal to 2 and this is your n is equal to 4. Electron initially is present in n is equal to 4. And the atom which we are talking about, that's hydrogen. That's hydrogen. Okay? That's hydrogen. Electron initially was in n is equal to 4. Now the electron is moving from 4 to 2. 4 to 2. We know when the electron makes a transition from higher to lower, it emits energy. It emits energy. How much it emits? Whatever is the energy gap between the two shells, same amount of energy electron will be emitting. Perfect. Now, first of all, what is the energy carried by the electron when it is in 4th energy shell, E4? How do we calculate it? E is equal to minus 13.6 Z square divided by N square. Z is equal to 1. N is equal to 4. So energy of the electron in the 4th energy state, 1, 2, 3, 4. It is minus 0.85. It is minus 0.85 electron volts. And energy carried by the electron when it is in 2nd energy state. when it is in n is equal to 2. In n is equal to 2, it is minus 3.4. It is minus 3.4. Minus 3.4 electron volts. Now the electron is coming from 4 to 2. It is going to emit energy. How much? The difference between the two energy shells. So delta E will be equal to E2 minus E4. E2 minus E4. E2 is minus 3.4. E4 is minus 0.85. How much this value comes out to be after solving? Can you quickly check it? E2 and E4, gap. Gap between E2 and E4. How much this value comes out to be? Is it coming out to be, I think 2 point something, 2.6 something approximately, or 2.5? Let me take it as 2.5. So this much energy is emitted when the electron is coming from 4 to 2. When the electron is coming from 4 to 2, it is emitting how much energy? 2.5 electron volts it is emitting. Right? Now this energy which is emitted by the electron, when it is coming from 4 to 2, this amount of energy is emitted by the electron. Now this amount of energy is incident on some metal. This amount of energy is incident on some metal. So you have got a metal surface, right? On this metal surface, how much energy is incident? Same amount of energy is incident. 2.5 electron volts energy is incident, right? Work function of this metal, phi naught, is equal to, I think this is 2.55 electron volts. Just a second. This is 2.55 electron volts. This is 2.55 electron volts. Phi naught is 2.5 electron volts. Now, when this much of energy is incident on the metal, electron will be ejected, right? So kinetic energy possessed by that electron would be equal to how much? I would simply use the equation which we have already discussed. EI is equal to phi naught plus KE max, right? So your KE max from here would be equal to how much? KE max from here would be equal to 2.55 minus 2.5, right? Which will be 0.05 electron volts. 0.05 electron volts. So you got the kinetic energy, maximum kinetic energy of the electron in electron volts. But we need the answer in joules. So what do you need to do? 1 electron volt is how much? 1 electron volt is 1.6 into 10 raised power minus 19 joules. So solve this and get the maximum kinetic energy possessed by the electron. Am I clear? Am I clear, people? Did you understand the question? Did you understand the question? Let me know once in the chats, everybody. Let me know once in the chats, everybody, if it is clear. Let me know once in the chats quickly, everybody. Yeah, all clear? All clear, guys? Now, let's talk about hydrogen spectrum now. This is something important. Let's say this is the ground state of hydrogen, n is equal to 1. Let's say this is n is equal to 2 of hydrogen, the first energy state. Let's say this is the n is equal to 3 of hydrogen, the third energy state. Let's say this is the n is equal to 4 for hydrogen. This is n is equal to 4. Let's say you have got n is equal to 5 here. N is equal to 5. Let's say you have got n is equal to 6 here. N is equal to 6. Okay. Let's say you have got, let's say you have got n is equal to infinity over here. Perfect. My dear students, let me tell you one thing. In case of hydrogen atom, electron is present in shell number 1. Okay. In case of hydrogen atom, electron is present in shell number 1. If we supply some energy to that electron, where do it go? Where does it go? In case of hydrogen, electron is present in ground state. N is equal to 1. If we supply some energy to the electron, can I say the electron will get excited? It will go to higher energy state. Now, in the higher energy state, electron is not very stable. In higher energy state, electron is not very stable. Electron only resides there for 10 raised power minus 8 seconds. When electron moves to higher energy state, at higher energy state, electron is very unstable. It just remains there for 10 raised power minus 8 seconds and jumps back and jumps back and jumps back. And when the electron jumps back from higher energy state to lower energy state, it emits energy in the form of radiations. It emits energy in the form of radiations, right? And my dear students, when the electron makes a transition, from higher energy states to shell number 1, when the electron makes a transition from higher energy states to shell number 1, like this. When the electron makes a transition from higher energy state to shell number 1, we get a series of radiations. This is your one radiation, one more radiation. When electron falls from 3 to 1, when it falls from 4 to 1, one more radiation. We get a series of radiations. And those series of radiations which we get here is what you call as Lyman series. Similarly, when the electron makes a transition from higher energy state to shell number 2, when the electron makes a transition from higher energy state to shell number 2, again we get a series of radiation, right? And this series of radiations is what you call as Balmer series. Okay. Similarly, when the electron makes a transition from higher to shell number 3, what do we get? Again, we get a series of radiations. That's what you call as Paschen series. Lyman, Balmer, Paschen. Similarly, bracket and fund. So bracket series is when electron makes a transition from higher to shell number 4. This is your bracket series. Okay, this is your bracket. Similarly, your fund series, when electron makes a transition from higher energy state to shell number 5. This is your fund, PFUND. Similarly, when the electron makes a transition from higher energy state to shell number 6, that's what you call as Humphrey series. Now guys, here are a few terminologies which you need to know. What are those terminologies? Let's try to understand the terminologies. Which series this is? This is your Lyman series. This particular transition from 2 to 1, when the electron makes a transition from 2 to 1, it emits radiation. The radiation falls in what? It falls in Lyman series. This particular line over here is what you call either as first line of Lyman series, or you can call it as H alpha line. You call it either as first line of Lyman series, or you can call it as H alpha line of Lyman series. Similarly, this particular line is what you call as second line of Lyman series, or you can call it as H beta line of Lyman. Similarly, this is what you call as, again, your third line of Lyman series, fourth line of Lyman series, and so on, right? Similarly, when you talk about Balmer series, this particular line is what you call as H alpha line of Balmer, or you can call it as first line of Balmer. Similarly, second line of Balmer, third line of Balmer, and so on. Perfect. So I hope you got to know what are these terminologies: H alpha, H beta, H gamma, right? First line of Lyman, second line of Balmer, third line of Paschen, etc., etc. I hope you're clear with the terminologies now. My dear students, now comes a point. Since I told you, when the electron makes a transition from higher energy state to lower energy state, it emits energy in the form of radiation. It emits energy in the form of radiation. How do we calculate the wavelength of the radiation? How do we calculate the wavelength of the radiation which is emitted when the electron makes a transition from higher to lower energy state? For that, so first of all, I'm marking the heading as calculation of the wavelength. Calculation of wavelength emitted or absorbed. Emitted or absorbed during the transition. Emitted or absorbed during the transition. For that, we have got a formula. You must have heard about it as well. You call it as the Rydberg's formula. Rydberg's formula. Rydberg's formula is used to calculate the wavelength of the radiation emitted or absorbed during the transition. Okay? And what this Rydberg's formula says? My dear students, as per this Rydberg's formula is concerned, we can say wave number, which is nothing but 1 by lambda, is equal to R Z square 1 upon N1 square minus 1 upon N2 square. Remember this result. Remember this particular result. And let me tell you, this lambda is the wavelength emitted or absorbed during the transition of the electron. N1 represents the lower energy state. N2 represents the higher energy state. R is the Rydberg's constant. My dear students, remember the value of 1 by R. That is important. The value of R is not important. The value of 1 by R is important. And the value of 1 by R is nothing but 911.5 angstroms. This is the value of 1 by R. Okay? This is the value of 1 by R. Now, how do we exactly use this particular formula? Understand properly what exactly I'm going to say. Let's first of all try to analyze your Lyman series. From this, everything will be clear. In case of Lyman series, electron makes a transition from higher energy states to shell number 1. So people, understand. When the electron will be making a transition from higher energy state to shell number 1, it will be emitting energy in the form of radiation. That radiation would be having some wavelength, right? Those radiations which are emitted when the electrons make a transition from higher energy state to shell number 1, right? Those radiations emitted would be having some wavelength. Okay? If I ask you, calculate the shortest wavelength. Calculate the shortest wavelength emitted in the Lyman series. Shortest wavelength is also called as the series limit. Calculate the series limit. Calculate the shortest wavelength emitted in the Lyman series. Now, first of all, you know your delta E is inversely proportional to lambda. Basically, delta E is equal to hc by lambda, right? Delta E is inversely proportional to lambda. We have to calculate the shortest wavelength. For the wavelength to be shortest, energy gap should be maximum. And in case of Lyman series, when is the energy gap maximum? In case of Lyman series, energy gap is maximum when the electron makes a transition from infinity to 1. Perfect. So you got the transition. Infinity. This is my lower energy state. This is my higher energy state. Now use the Rydberg's formula. 1 by lambda is equal to R Z square. Since I'm talking about hydrogen, for hydrogen Z is 1. 1 upon N1 square minus 1 upon N2 square. 1 upon infinity is 0. So 1 divided by lambda is equal to R, or I can say lambda is equal to 1 by R, and 1 by R is nothing but 911.5 angstroms. So this is the wavelength emitted when this is the shortest wavelength emitted during the Lyman series, in the Lyman series. Okay? Perfect. Similarly, if I ask you to calculate the longest wavelength emitted in Lyman series, calculate the longest wavelength emitted in Lyman series. For the wavelength, for the lambda to be longest, delta E has to be minimum. Delta E has to be minimum. And in case of Lyman, when is delta E minimum? In case of Lyman, when is delta E minimum? When is energy gap minimum? When the transition is from 2 to 1. When the transition is from 2 to 1. Okay? See, 2 to 1, 3 to 1, 4 to 1, 5 to 1. When is the energy gap minimum? When the transition is from 2 to 1. Lower energy state here is N1. This is your higher energy state. So 1 divided by lambda is equal to R. Z square, that's 1. 1 upon N1 square minus 1 upon N2 square. Matter of calculation, 1 by lambda is equal to R. This is 1 minus 1 by 4. So 1 divided by lambda is equal to R. 4 minus 1 is 3. So 3 by 4. So I can say 1 divided by lambda is equal to 4 divided by 3 multiplied by 1 by R. So 1 by lambda is equal to 4 by 3. 1 by R is nothing but 911.5 angstroms. Right? Sorry, this lambda here. Okay? Lambda is equal to 4 by 3 into 911.5 angstroms. So this is how you calculate shortest wavelength and the longest wavelength in any series. Okay, for example, I'm asking you to calculate the shortest wavelength in Balmer. Just tell me the transition in the chats. Shortest wavelength in Balmer. Shortest wavelength in Balmer. Tell me the transition. Shortest wavelength in Balmer. Tell me the transition. Quick. Shortest wavelength in Balmer. Tell me the transition. Everybody. Shortest wavelength means maximum energy gap. In Balmer, when is the energy gap maximum? When the transition is from infinity to 2. Infinity to 2. Okay? Infinity to 2. Perfect. Tell me the longest wavelength in Balmer. To calculate the longest wavelength in Balmer, tell me the transition. To calculate longest wavelength in Balmer, tell me the transition. Longest wavelength means minimum energy gap. Minimum energy gap in Balmer is 3 to 2. Perfect. Right? Perfect. Amazing. Good. So I hope you got this, huh? I hope you got this calculation. Now, if you got this calculation, there is one more thing which you need to know. This particular table. My dear students, what is the Lyman series? In Lyman series, electron makes a transition from higher energy state to shell number 1. It can be 2 to 1, 3 to 1, 4 to 1, 5 to 1. In every transition, radiation is emitted. In every transition, radiation is emitted. In Lyman series, all the radiations which we get, they fall in ultraviolet region. Okay? They fall in ultraviolet region. In the Balmer series, whatever radiations we get, they fall in visible region. In the Paschen series, infrared, bracket infrared, fund infrared, right? This also infrared. So how you are going to remember it? UVIII. UVIII. Ultraviolet, visible, infra. Okay? Perfect. So the radiations which we get in Balmer series, they fall in visible region. And this was once question asked in your NEET examination. The radiations which we get in Balmer series, in which region do we get them? We get them exactly in visible region. Right? This table is also equally important, so remember this. Now here is one more thing which I would want to share with you. What is that? That's also one important thing, and after that I can give you some questions on it. See guys, calculation of maximum spectral lines. Maximum number of spectral lines when the electron makes a transition from higher to lower. Calculation of maximum number of spectral lines when the electron makes a transition from higher to lower is given by the formula N2 minus N1 plus 1, N2 minus N1 divided by 2. This is one very important formula with the help of which we can calculate the maximum number of spectral lines obtained when the electron makes a transition from higher energy state to lower energy state. Higher to lower. Okay. For example, I'm telling you that electron is making a transition from 6 to 1. Electron makes a transition from 6 to 1. I'm asking you to calculate the total number of spectral lines produced. Say, this is your lower energy state, N1. This is your higher energy state, N2. Perfect. Calculate the total spectral lines. It is going to be N2 minus N1. Total number of spectral lines would be equal to N2 is 6 minus N1 plus 1. N2 minus N1 divided by 2. So it is going to be equal to this term cancels. So 6 into 5 is 30. 30 divided by 2 is 15. So I would say in total 15 spectral lines would be obtained. Right? Now guys, this is okay. You guys know it already. But the point is something different. Out of these 15 spectral lines, how many will fall into Lyman? How many will fall into Balmer? How many will fall into Paschen? How do we get that? Remember this result. Spectral lines in a particular series is equal to. It's going to be always higher energy state minus ground state of that particular series. Higher energy state minus ground state of that particular series. What does it exactly mean? Have a look. Electron is going from 6 to 1. So how many spectral lines in total? 15. Let's now get to know out of 15, how many will fall into Lyman? How many will fall into Balmer? How many will fall into Paschen? Right? So out of these 15, how many will fall into Lyman series? It's equal to N2. N2 is the higher energy state, that is 6 minus ground state of Lyman. What is the ground state of Lyman? 1. So 6 minus 1 is 5. So out of 15 spectral lines, 5 will fall into Lyman. How many will fall into Balmer? N2, that is 6 minus the ground state of Balmer. Ground state of Balmer is 2. So 6 minus 2 is 4. Paschen series. N2 is 6 minus the ground state of Paschen. This was 1, 2, 3. So 6 minus 3 is 3. Lyman, Balmer, Paschen. Bracket series. 6 minus 4. That is 2. Paschen series. 6 minus 5. That is 1. Okay. If you make a total of these, 5 plus 4 is 9. 9 plus 3 is 12. 12 plus 2 is 14. 14 plus 1 is 15. So in total, 15 spectral lines are produced. Is this particular point clear? Tell me once in the chats, people. Is this particular point clear? Is this particular point clear to everybody? I want to know in the chats. Perfectly done. And if this is perfectly done, let's try to solve one question so that I'll get to know that you got the concepts or not. This is one question which we have. Check it out. What transition in the hydrogen spectrum? What transition in the hydrogen spectrum would have same wavelength as the Balmer transition? N is equal to 4 to N is equal to 2 in case of He positive. So in case of He positive, electron is making a transition from 4 to 2. In case of He positive, electron is making a transition from 4 to 2. So it will be emitting the radiation, which would be having some wavelength. Let the wavelength of the radiation emitted is lambda. Right? What will be the transition in hydrogen? What would be the transition in hydrogen such that the radiation emitted here would have the same wavelength? I hope you understood the question. What should be the transition here in case of hydrogen such that the wavelength emitted is same as that of this particular one? How do you get it? See guys, for hydrogen I can write 1 by lambda is equal to R Z square. Z is 1. 1 upon N1 square minus 1 upon N2 square. Okay, write the same equation for this. It's going to be again 1 divided by lambda is equal to r. Z for helium is 2. 2 ka square is 4. R Z square, right? So it's 4. 1 upon n1 square. 2 ka square 4. 1 upon n2 square. 4 ka square 16. So it's 1 divided by lambda is equal to r. Take this 4 inside. So it becomes 1 by 1. Take this 4 inside. It becomes 1 upon 4. Or I can write it like this. 1 by lambda is equal to r. This is going to be 1 upon 1 ka square. This is going to be 1 upon 2 ka square. Now, my dear students, look at these two equations. This one and this one. Just compare these two. Just compare these two equations. When you compare these two equations, this n1 square, this 1 square. That means the value of n1 here has to be 1. n2 square, this 2 square. That means the value of n2 here has to be 2. So you got n1, n2. So basically in hydrogen, the transition should be from 2 to 1. In hydrogen, the transition has to be from 2 to 1. Then only the wavelength emitted here and the wavelength emitted here would be the same. Did you understand this question? Did you understand the question, people? Everybody? Everybody in the chats? By the way, your GOC session is live. Okay? GOC session is live. Let me check whether it's live or not. Yes, this is your general organic chemistry session. And I'm going to take this session on live in 3 days. 14th. 14th means Friday. Friday I'll be taking this session. This will be complete GOC, like 3-4 hours. Got it? Okay. I want everyone to click here on notify me right now. Right now means right now. Go to this session first. Otherwise you'll forget. I know that. I don't want you guys to forget. Click on notify me right now, everybody. Done? This class is enough. Perfect. I'm moving on. I am moving on then. I am moving on. All right, guys, look at this question. What do you think? What do you think about this question? Hydrogen atom in ground state. Guys, I know you are tired. Just let's solve few questions. I'll give you the break for 10 to 15 minutes, okay? But maximum 10 to 15 minutes. Hydrogen atom in ground state. Hydrogen atom in ground state. Ground state means N1 is 1. Is excited by monochromatic radiation of wavelength lambda, right? Due to which it is going to some higher energy state N2. On coming back to ground state, 15 different spectral lines were observed. On coming back to ground state, 15 different spectral lines were observed. Calculate lambda. First of all, how many spectral lines are observed in total? 15 spectral lines. How do we calculate spectral lines? N2 minus N1, N2 minus N1, N2 minus N1 plus 1 divided by 2 is equal to 15. I would say N2 minus 1. This would be N2 because this 1 gets cancelled. 15 2 is equal to 30. So what has to be the value of N2? N2 should be 6. So that this is 6. 6 minus 1 is 5. So 6, 5 comes out to be 30. Yeah. So N2 here is equal to what? N2 here is equal to 6. So I got to know the higher energy state. Higher energy state is what? It is 6th energy state. What do we have to calculate? Lambda. Now we already know electron, the transition is between 1 to 6. So we know 1 by lambda is equal to R. Since we are talking about hydrogen, so Z is 1. 1 upon N1 square minus 1 upon N2 square. Just the matter of calculation. 1 by lambda is equal to R. So 1 upon 1 minus 1 upon 6 square, 36. So 1 divided by lambda is equal to R. So 36 minus 1 is 35 divided by 36. Take the reciprocal. Lambda is equal to 36 divided by 35 multiplied by 1 by R. So it is 36 divided by 35. 1 by R is nothing but 911.5. Just matter of calculation. Solve it and get the answer in angstroms. That's it. Got it? Got it, people? Got it, got it, got it. Everybody. Everybody in the chats. Is it clear? If this is clear, tell me the answer of this question. If this is clear, tell me the answer of this question. Electron in the hydrogen atom. Electron in the hydrogen atom jumps from higher level that is N2 to third energy level. If 6 spectral lines are observed, find out the initial position. This is simple. Nothing to do here, right? So it's going to be simply N2 minus N1, N2 minus N1 plus 1 divided by 2 is equal to 6. So it's N2 minus 3. This is going to be N2 minus 2 is equal to 6 2s are 12, right? Matter of calculation. Yeah. If N2 is 6, 6 minus 3 is 3. If N2 is 6, 6 minus 3 is 3. 6 minus 2 is 4. 4 into 3 is 12. So N2 has to be 6, okay? N2 has to be 6. Got it? This is how you solve these questions. Perfect. So let me give you the break for 10 minutes and then we'll be starting the de Broglie's hypothesis. Guys, 2 more hours left. 2 more hours left. I want every one of you to be back on time. Okay? I want every one of you to be back on time. So break till, what is the time now? It is 10:05. Break till 10:20. A 15-minute quick break I'm giving. I'll be exactly starting back at 10:20. And I would want every one of you to be back on the time. Okay? See you in a while. Take care. Are you all back? Are you all back? Yes. Back with the same energy or not? Back with the same energy or not? Back with the same energy or not? Quickly in the chats, everybody. Yeah, full energy. Seems that's great. Where am I? I'm right now live from Srinagar, Jammu and Kashmir. Perfect, guys. So let's have a look on one more important topic, that is your de Broglie's hypothesis, right? This again one topic which you study frequently in your physics as well, right? First of all, this de Broglie's hypothesis, let me tell you, it explains the dual nature of the matter. It explains the dual nature of the matter. As per this hypothesis, matter can also behave as a wave. Matter can also behave as a wave, right? And the wave nature of matter was experimentally proven by Davison-Germer experiment. Well, I'm not going into the details of Davison-Germer. That is something which you'll study in physics. Right now, what is my point of discussion? Let's have a look on that. My dear students, let's say this is one microscopic particle, a very, very, very small particle, okay? A very small object. It has got some mass m. A very small object having mass m. Let's say this very small object is moving with some velocity v. Let's say this very small object, which has got mass m, is moving with some velocity v. You have got the small object having mass, having velocity. Mass multiplied by velocity, what do we call this as? Momentum. We call this as linear momentum. So this particular small object, I would say it has got momentum, right? And momentum is the characteristic of which nature? Momentum is the characteristic of the particle nature. Momentum is the characteristic of what? It is the characteristic of the particle nature. De Broglie's hypothesis, what exactly is all about? As per de Broglie, whenever you will have the object moving with certain velocity, when the object will be moving with certain velocity, there will be a wave associated with this object as well. There will be a wave associated with the object as well. Okay? And if you have got the object moving with certain velocity, as per de Broglie, whenever the object having certain mass moving with certain velocity, let me tell you, as per de Broglie, it would be having a wave associated with it as well. You call this wave as the matter wave. Or you can simply call it as the de Broglie's wave. Okay? Perfect. Now, since this is a de Broglie's wave, it's a matter wave. So it will be having some wavelength as well. And this object, which has got some mass moving with certain velocity, it has got some momentum as well. De Broglie related the wavelength of the matter wave and the momentum of this particular object. And as per de Broglie's hypothesis concerned, he said lambda has to be inversely proportional to the momentum. Lambda has to be inversely proportional to the momentum. Okay? The wavelength of the de Broglie's wave associated with the object has to be inversely proportional to the momentum of this particular object. Perfect. This is the result which you have to remember. That's all. Nothing more than this. Okay? Now, my dear students, when you remove the proportionality sign, what do you get? Lambda is equal, it's going to be h divided by p. Lambda is equal to h divided by p. So I've got one important result over here, which I'm going to utilize in the questions. Lambda is equal to h divided by p, or you can say lambda is equal to h divided by p is nothing but m multiplied by v. P is nothing but m multiplied by v. Now, my dear students, one more thing. You would have sometimes studied like this. Kinetic energy of a particle is always equal to p square divided by 2m. I hope this result you would have studied somewhere. So can I eliminate p from here? P is going to be under root of 2m multiplied by kinetic energy. So instead of p, I can write h divided by under root of 2m multiplied by kinetic energy of the particle. Okay. Perfect. So first result is in terms of momentum. Second result is in terms of kinetic energy. Now, my dear students, one more thing. Let me tell you, if a charged particle is accelerated, under some voltage V, if a charged particle is accelerated under some voltage V, at that point of time, lambda is equal to h divided by under root of 2m. Instead of kinetic energy, you'll write q, charge on the particle, multiplied by potential difference under which the particle is accelerated. This is one more important result which you have to remember. Now, one more thing. Let me tell you, if the charged particle in particular is electron, so I'm saying if an electron is accelerated, under some voltage V, then lambda will be equal to, if you put the value of h, 6.6, mass of electron, 9.1 into something, charge on electron, 1.6 into something, right? The final result comes out to be 12.27 divided by under root of V, where V is the potential difference under which the electron has been accelerated. This result is only valid for electron. This electron is valid for all the charged particles which are being accelerated under some voltage. Perfect. So, my dear students, these are few results which I would want you guys to remember. Number one. Number two. When the electron revolves around the nucleus. When the electron revolves around the nucleus, can I say the direction of electron continuously keeps on changing? So can I say this electron is under accelerated motion? The electron is under acceleration because its direction is continuously changing, right? Perfect. Now, my dear students, one thing which you have to analyze here. See, first of all, understand what I'm going to say. This is the particle. It has got some mass. It has got some velocity. It's moving. So as per de Broglie, this particle should have a wave associated with it as well. You call that wave as the de Broglie's wave. So when the electron revolves around the nucleus, perfect, it will be having a wave nature as well. Now try to understand what do I say. I have given you the result MVR is equal to NH divided by 2 pi. This is one of the results which I have given you. MVR is equal to NH divided by 2 pi. If I write something like this, 2 pi R, I have taken 2 pi here. 2 pi R is equal to NH divided by MV. Or I can say 2 pi R is equal to N. H upon MV is nothing but lambda. So this is one more important result which you need to remember over here. 2 pi R is equal to N lambda. You would have studied many a times. 2 pi R is equal to N times lambda. Okay. From this particular result, if a question comes, number of waves made by an electron in a shell, when the electron is moving in some shell, is always equal to N. remember this particular result as well. What does it mean? See, if the electron moves in shell number 1, it will be creating one wave. If the electron is moving in shell number 2, the waves produced by the electron is 2. If the electron is moving in shell number 3, number of waves made is equal to 3. If the electron is moving in shell number 4, number of waves made is equal to 4. So this is all what you need to remember. From all these results, questions can be framed. For example, let's have a look on this basic question. And I believe you can easily kill this one. The question is, if the kinetic energy of the proton is increased 9 times, the wavelength of the de Broglie's wave associated with it would become. What do you think? Since you know your lambda is equal to h divided by under root of 2m multiplied by kinetic energy. Or in short, I can say lambda is inversely proportional to what? Root of kinetic energy. Lambda is inversely proportional to root of kinetic energy. Or let me write it completely. Okay. Now, my dear students, let me call this as lambda 1. Let me call this as Ke1. Okay. Now, the question says, if the kinetic energy of proton is increased 9 times, what would be the lambda 2? So, I'll say lambda 2 will be h divided by under root of 2m. Now, it's going to be 9 times kinetic energy. Okay. It's going to be 9 times kinetic energy. Or you can say lambda 2 is equal to h divided by 9 root. So, take 3 out. Under root of 2m multiplied by kinetic energy. H divided by 2m kinetic energy. H divided by 2m kinetic energy. Okay. H divided by 2m kinetic energy is nothing but lambda 1. So, it's going to be lambda 1 divided by 3. So, when the kinetic energy is increased 9 times, the wavelength of the de Broglie's wave has become 1/3 of the initial wavelength. 1/3 of the initial wavelength. Am I clear with this? A very simple and basic question this is. Right? And these sort of questions are asked in your exam. Okay, you have got one more question like this. Try to analyze this question. In the hydrogen atom, if x is the radius of first Bohr's orbit, first of all, radius of nth Bohr's orbit is nothing but r0 n square divided by z. Since we are talking about hydrogen, so z is 1. Z is 1. And we are talking about the first Bohr's orbit of hydrogen. So n is also 1. So I will say R1 is equal to R0. And as per the question, it is equal to X. As per the question, it is equal to X. Now the question says, the de Broglie's wavelength of the electron in the third orbit. De Broglie's wavelength of the electron in the third orbit. Right now I gave you one result. 2 pi r is equal to n lambda. 2 pi r is equal to n lambda. So I'll say 2 pi. What is the radius of the electron in the first orbit of hydrogen? That is x. That is x, right? Right now we have to talk about which orbit? We have to talk about third orbit. So I can say 2 pi. Instead of Rn, I'll write R0 n square divided by z is equal to n times lambda. So I'll write 2 pi. R0 is nothing but x. N over here is 3. 3 ka square is 9, right? Z value is 1. N value is 3. And this is lambda, right? So 3, 1, 3, 3. 3 2s are 6. So 6 pi x is coming out to be the value of lambda. This is something I was supposed to calculate. Is this clear? Did you understand how I solved? In hydrogen atom, x is the radius of first Bohr's orbit. Okay? De Broglie's wavelength of the electron in the third orbit. De Broglie's wavelength of the electron in the third orbit. I use this particular result. 2 pi r. This is the radius of the third orbit. Is equal to the third orbit multiplied by lambda. Radius of third orbit I used with the help of this particular result, right? I just have put the values here and I got the value of lambda, and lambda is coming out to be nothing but 6 pi x. Okay? These are different types of questions which can be asked. Now, my dear students, there is one more important topic. Well, from this topic, it's been like 4 or 5 years questions have not been asked. But this year maybe question can be asked from this topic. And it's simple. What this Heisenberg's uncertainty principle is all about. Look at the definition. Look at the statement. According to the principle, the momentum and the position of a moving electron of a moving electron, of a microscopic particle like electron, cannot be determined simultaneously with 100% accuracy. The momentum and the position of a microscopic particle like electron both cannot be calculated simultaneously with 100% accuracy. Both cannot be calculated simultaneously with 100% accuracy. If you try to measure momentum with 100% accuracy, there will be error or uncertainty in position. There will be error or uncertainty in the position. If you want to locate the position of the electron with 100% accuracy, there will be error or uncertainty in the momentum. So both the things cannot be calculated with 100% accuracy, that too simultaneously. If you try to calculate one with 100% accuracy, there will be error in another one. There will be error in another one. Okay? And let me tell you, error in the position is represented by delta x. Delta x represents your error in the position. Delta v represents error or uncertainty in the velocity. Your delta p, which is basically, what is p? P, you know, p is nothing but m multiplied by v, right? So error in momentum will be due to error in velocity. So I'll say delta p is nothing but m delta v. Perfect. Delta p, error or uncertainty in the momentum. And this delta p is nothing but m delta v. Perfect. Similarly, you know this lambda. What is lambda? Lambda is equal to h upon mv. Lambda is equal to h upon mv. H is constant, m is constant. So if there is error in de Broglie's wavelength, it will be due to the error in velocity. If there is error in de Broglie's wavelength, that will be due to the error in velocity. So I'll say error in de Broglie's wavelength will be equal to h upon m delta v. So there is one more term which I'm writing over here, that is delta lambda, which represents error or uncertainty in the de Broglie's wavelength. Okay, which is nothing but h upon m delta v. H upon m delta v. Okay, right? So people, again, let me quickly give you the recap of this. When the electron will be moving around the nucleus, okay, if you want to calculate the momentum of the electron with 100% accuracy, if you want to calculate momentum of electron with 100% accuracy, at the same time, no doubt, you're trying to calculate the momentum of electron with 100% accuracy, there will be error in its position. If you want to get the position of the electron with 100% accuracy, there will be error or uncertainty in its momentum. So position and momentum of the microscopic particle cannot be determined simultaneously with 100% accuracy. If you want to calculate one with 100% accuracy, there will be error in another one. There will be error in another one. Okay? So both the things cannot go hand in hand. And mathematically it has been observed, delta x dot delta p, it is greater or equal to h upon 4 pi. You need not to know from where this result comes. You just have to remember it. Okay? Delta x dot delta p is greater or equal to h upon 4 pi. Or instead of delta p, you can write m delta v. You can write m delta v. That m goes into the denominator here. So you got one more result. Delta x dot delta v is greater or equal to h upon 4 pi m. There is one more result. Delta x dot delta lambda is greater or equal to lambda square divided by 4 pi. Okay? These are the three results which you have to remember directly. Basically, there is a derivation for this particular result. We can derive this as well, but there is no need for derivation right now. Okay? Derivation won't be asked, but these three results can be directly asked. Delta x delta v greater or equal to h upon 4 pi, number one. Delta x delta v greater or equal to h upon 4 pi m. Similarly, delta x delta lambda greater or equal to lambda square divided by 4 pi. These are the three results which you have to remember directly. Okay? Now, my dear students, what kind of question can be asked from this? What kind of question can be asked from this? There can be two types of questions asked here. Number one. First of all, let me tell you one thing. Whenever a question is asked from Heisenberg's uncertainty principle, I'll always go as per SI system. I'll always take all the values as per SI system. For example, a particle with mass 10 raised power minus 10 grams. Okay. What is the SI unit of mass? Kg. So I'll be writing as 10 raised power minus 10 divided by 10 raised power 3, right? So it comes out to be 10 raised power minus 13 kg. Now this is as per SI system. Okay. We have got a particle. We have got a particle whose mass is 10 raised power minus 13 kg. If the velocity of the particle, velocity of the particle is 10 raised power minus 6 centimeter per second. Centimeter per second. It's not as per SI system. It has to be meter per second. So it's going to be 10 raised power minus 8 meter per second. Okay. With the uncertainty, error in velocity, delta V, is equal to 0.0001%. So 10 raised power minus 4%. Error in the velocity is 10 raised power minus 4% of its actual velocity. Right? Error in the velocity is 10 raised power minus 4% of its V. Okay? So, if I need to calculate delta V, it's 10 raised power minus 4% of V. V is 10 raised power minus 8. So, this becomes 10 raised power minus 12 divided by 100. So, it becomes 10 raised power minus 14 meter per second. This is the error in the velocity. This is the error in the velocity. So, if I ask you what would be the actual velocity would be equal to 10 raised power minus 8 plus minus 10 raised power minus 14. This would be the actual velocity. Okay. Now, what do I need to do? What do I need to calculate? I need to calculate delta x, error in the position. You know already, your delta x dot delta v, it has to be greater or equal to h upon 4 pi m. So, what do I need to calculate? Delta x, which has to be equal to greater or equal to h upon 4 pi m multiplied by delta v. So, h is nothing but 6.6 into 10 raised power minus 34. 4 pi is your 22 by 7. M is 10 raised power minus 13. And delta v, error in the velocity, is 10 raised power minus 14. Matter of calculation. Solve this. The answer is going to come in meters. Because I have taken all the parameters as per SI system. Am I clear with this? Am I clear with this? Simple formula based question this is. Nothing else. I just have to put the values. That's it. I just need to put the values in the equation. That's it. For example, we have got one more question. Look at this question. The question says if the error in velocity and position is same, so delta v is equal to delta x, what would be the error in de Broglie's wavelength? What would be the error in de Broglie's wavelength? We have to calculate delta lambda. Delta x, delta v, both are same. We have to get the value of delta lambda. I already told you one thing. Your delta lambda is nothing but h upon m delta v. H upon m delta v. So, in order to get the value of delta lambda, I need to get the value of delta v. How do I get the value of delta v? Try to understand. We already know delta x dot delta v is greater or equal to h upon 4 pi m. Now, delta x, delta v, they are equal. So, I can write delta v ka square is greater or equal to h upon 4 pi m. So, therefore, I can say delta v is greater or equal to under root of h upon 4 pi m. This is delta v. Now, you got the delta v. Put the value of delta v here. So, it's going to be h divided by m. What is delta v? Delta v is under root of h upon 4 pi m. Perfect. Now, if I take the square as common, so this h becomes h square divided by this m becomes m square, right? Rest everything is same, h upon 4 pi m, right? So, my dear students, delta lambda has to be equal to under root of this h cancels out, m gets cancelled out, 4 pi goes up. So, 4 pi h divided by m is the final answer of the question. This is the value of delta lambda, which I was supposed to calculate. Look at this. This is how you guys are going to solve these sort of questions. Do you understand? Do you understand, people? Do you understand? Yes or no in the chats, everybody. Yes or no in the chats, everyone. Everyone in the chats. Is it clear? Everyone. Perfect. Now, my dear students, we are going to enter into one more part of the chapter. That is your quantum numbers, like your favorite topic. Your favorite topic, yeah? Quantum numbers. What are quantum numbers basically? Let me first of all tell you, quantum numbers, these are the set of four numbers. Set of four numbers, which give us the exact information about an electron in an atom. The set of four numbers which give us the complete information about an electron in an atom. Okay? So I will say these are the set of four numbers required to locate the electron in an atom. Perfect. Now we have got four quantum numbers. One is your principal, second is azimuthal, magnetic, spin quantum number. So we have got four quantum numbers. Out of these four quantum numbers, the first three quantum numbers, out of the four quantum numbers, the first three, they are the outcome of Schrodinger's wave equation. They are the outcome of Schrodinger's wave equation. The first three quantum numbers, basically, they are the outcome of the Schrodinger's wave equation. Okay, just remember it as such. One by one, I'll discuss these quantum numbers with you. The first quantum number is your principal quantum number. One of the simplest, principal quantum number. My dear students, principal quantum number, which we represent with n, Let me tell you, it represents the size and energy of the shell. Principal quantum number, it represents the size and energy of the shell. As the value of n increases, size as well as energy of the shell keeps on increasing. Principal quantum number, which we represent with n, it represents the size and energy of the shell. Or let me simplify it for you. See, remember one thing. Principal quantum number, it gives us the idea about the shell number in which the electron is present. You know, your shells consist of subshells. Subshells consist of orbitals, right? Shells consist of subshells. Subshells consist of orbitals. Principal quantum number is going to let us know in which shell electron is present. Principal quantum number is going to let us know in which shell electron is present. So n can be 1, n can be 2 for the electron, n can be 3 for example, n can be 4 for example. If I say n is equal to 1 for electron, that means the electron is present in the first shell, which is what you call as K shell. If n is equal to 2 for electron, that means the electron is present in the second shell, which is what you call as L shell. This is the third shell, M shell. This is the fourth shell, that is your N shell. So your principal quantum number is going to let us know exactly in which shell the electron is present. In which shell the electron is present. Whether the electron is present in first shell, second shell, third shell, fourth shell, who is going to give us the idea about that? It is the principal quantum number. It is the principal quantum number, right? Perfect. And principal quantum number, it represents the size as well as energy of the shell. As the value of n increases, the size of the shell increases as well as the energy of the shell also increases. Okay? And people, this is something which you would be studying from class 9th. The maximum number of electrons which can be present in a particular shell is equal to what? 2n square. Maximum number of electrons which can be present in a particular shell is always equal to 2n square. Okay? Well, principal quantum number, it's not that important. Important is azimuthal quantum number and magnetic. Important is azimuthal and magnetic. Well, this azimuthal quantum number, let me tell you, it gives me the idea about the subshell in which electron is present. This azimuthal quantum number L, it gives me the idea about the subshell in which electron is present. In which electron is present. How exactly? That's what I'm going to discuss with you. See guys, if I talk about this azimuthal quantum number L, which is going to let me know in which subshell of a particular shell electron is present. In which subshell of a particular shell electron is present. That azimuthal quantum number is going to tell me. How exactly? Say, the value of L, is from 0 to n minus 1. The value of L is from 0 to n minus 1. Number 1. Number 2, every value of L represents subshell. Every value of L represents a subshell. Every value of L represents a subshell. At the same time, remember, L is equal to 0 represents S subshell. L is equal to 1 represents your P subshell. L is equal to 2 represents your D subshell. L is equal to 3 represents your F subshell. Represents your F subshell. Okay. L is equal to 0 represents S subshell. L is equal to 1 represents P. L is equal to 2 represents D subshell. L is equal to 3 represents your F subshell. Now guys, let's try to analyze this properly. See, for example, I've got the first shell. In case of your K shell means your N is equal to 1. Your N is equal to 1. We are talking about shell number 1. If N is equal to 1, what can be the value of L? L is from 0 to n minus 1. So 0 to 1 minus 1, 0. That means we got only one value of L. And that value of L is equal to 0. And L is equal to 0 represents your S subshell. L is equal to 0 represents your S subshell. So it means that in your first shell, there is only one subshell, which is what you call as S subshell. In your first shell, there is only one subshell present, which is your S subshell. My dear students, in your second shell, second is your L shell, right? For L shell, N is equal to 2. For second shell, N is equal to 2. Let's get to know how many subshells are present in N is equal to 2. Have a look. L is equal to 0 to n minus 1. 0 to 2 minus 1, which means L value is 0 and L value is 1. We got two values of L. And every value of L represents a subshell. And you know, L value is equal to 0 represents your S subshell. L value is equal to 1 represents your P subshell. So basically, in your L shell, there are two subshells. One is your S subshell, one is your P subshell. Okay? In your second shell, there are two subshells, S subshell, P subshell. Right? Perfect. Similarly, my dear students, let's say you have got a third shell. Third shell is M shell. In case of your M shell, N value is equal to 3. N value is equal to 3. If N is equal to 3, L can have how many values? L can have values between 0 to n minus 1. 0 to 3 minus 1. So it's going to be 0, 1 or 2. 0, 1 and 2. L is equal to 0 represents S subshell. This represents P. This represents D. So basically in your third shell, there are three subshells present. One is your S subshell, one is your P subshell, and one is your D subshell. Similarly, in case of your fourth shell, how many subshells will be present? 4 subshells. S, P, D, and F. Perfect. So your azimuthal quantum number, it gives us the idea about the subshells present in a particular shell. Okay. If you see carefully, in the first shell, there is one subshell. In the second shell, there are 2 subshells. In the third shell, there are 3 subshells. In the fourth shell, there are 4 subshells. Right? So remember, take a note of this. The number of subshells in a particular shell is equal to the value of n. The number of subshells in a particular shell is equal to the value of n. Okay? In the first subshell, in the first shell, 1 subshell. In the second shell, 2 subshells. Third shell, 3 subshells. Fourth shell, 4 subshells, etc., etc. Right? My dear students, one more important information this azimuthal quantum number gives us. What is that? What is that? That is about the orbital angular momentum. One more information this azimuthal quantum number gives us. What is that? It gives us the idea about the orbital angular momentum, which is calculated by the formula under root of L into L plus 1 h upon 2 pi. Under root of L into L plus 1 h upon 2 pi. For example, have a look. Let's say you have got 1s. Let's say you have got 2s. Let's say you have got 2p. Let's say you have got 3p. Let's say you have got 3d. I want to calculate their orbital angular momentums. This is s. In case of s, L value is 0. If L is equal to 0, put the value of L here. So this entire term becomes 0. So for 1s, orbital angular momentum is 0. Right? For 2s, again it's s, L value is 0. So orbital angular momentum has to be 0. In case of p, for p, L value is 1. If L value is 1, your orbital angular momentum is equal under root of 1 into 1 plus 1 h upon 2 pi, which comes out to be equal root of 2 h upon 2 pi, or you can say h upon under root of 2 pi. Perfect. This is the orbital angular momentum for 2p. Similarly, people, in case of 3p, for p, L is equal to 1. If L is equal to 1, orbital angular momentum again is going to be h upon root 2 pi only. Yes? Right? In case of 3d, for d, L is equal to 2. If L is equal to 2, so orbital angular momentum has to be equal to under root of L into L plus 1 h upon 2 pi. 2 plus 1 is 3, 3 2s are 6. So root of 6 h upon 2 pi. This is the orbital angular momentum of 3D. So this is how you calculate the orbital angular momentums as well. So do remember this. Do remember all of this. Okay? And the questions are directly asked. Calculate the orbital angular momentum of 3D, 4D, 5D, 6p, some whatever it is. So you should just know the formula and accordingly get the orbital angular momentum. Okay? Now, my dear students, comes one more important quantum number. What is that? That is your magnetic quantum number. See, principal quantum number gives us the idea about the shell number. Azimuthal quantum number gives me the idea about the subshell. Now, the magnetic quantum number gives me the idea about the orbital in which electron is present. Orbital, okay? Now, how exactly? First of all, this is some general information which you can see later on. Let me go into the actual stuff. Actual stuff is this. Your magnetic quantum number. It is going to tell me in which orbital electron is present. How exactly? For that, you need to remember the value of m lies between minus L to plus L. The value of m, magnetic quantum number, is between minus L to plus L. Number one. Number two, every value of m represents what? Represents the orbital. Every value of m represents the orbital. Okay? For example, in case of S subshell, what is the value of L? L value is 0 for S. If L is equal to 0, so m is going to be between minus 0 to plus 0, means m is equal to 0. So how many values of m did I get? I got one value of m. Every value of m represents an orbital. So basically it means that in S subshell, there is only one orbital, which is what I call as S orbital. Okay, in S subshell, there is only one orbital, which is what I'll be directly calling as S orbital. If I talk about the P subshell, in case of P, the value of L is 1. If the value of L is 1, m can have values minus 1 to plus 1. So it can be minus 1, 0, plus 1. So we got three values of m. And every value of m represents the orbital. So basically, in case of your P subshell, there are three orbitals. Okay? One is called as Px, one is called as Py, one is called as Pz. In case of your P subshell, there are three orbitals, Px, Py, Pz. Similarly, my dear students, in case of your D subshell, what is the value of L? L value is 2. If L is equal to 2, so value of m is going to be between minus 2 to plus 2. So minus 2, minus 1, 0, plus 1, plus 2. So how many values of m I got here? I got 5 values of m. 5, every value of m represents an orbital. So in case of your D subshell, how many orbitals are there? In case of D subshell, how many orbitals are there? There are 5 orbitals in D subshell. How do you name them? One is called as dxy, one is called as dyz, one is called as dxz, one is called as dx square minus y square, one is called as dz square. This is how you name them, right? Similarly, my dear students, in case of your F subshell, there would be 7 orbitals exactly. Similarly, in case of F subshell, there will be 7 orbitals. Okay, you need not to know their names, etc. So I'm scoring around 580 to 630 range in my mock tests. Even then, I'm feeling depressed. See, at this particular point, if you're scoring 580 to 630, it's a good score. It's a good score, right? So don't get demotivated or something. You're doing good. You are doing good. Okay? You are doing better than, I would say, you're doing better than 95% of the NEET 2025 aspirants. Perfect? Just keep that thing in mind. Surely, Jyotika, we'll do that. We'll do that. Perfect, guys. I believe everything is clear till here. I believe everything is clear till here. Is everything clear? Let me know once in the chats, everybody. Is everything clear till here? Let me know once in the chats quickly, guys. We do not have a lot of time. Okay, so I believe this stuff is clear. Now the last quantum number, which is what you call as your magnetic quantum number, right? Which is what you call as your magnetic quantum, your spin quantum number. Spin quantum number is represented by S or ms, okay? It will just give you the idea about the spin of the electron, whether the electron is going with clockwise spin or anti-clockwise spin. That's it. The spin quantum number is going to give you the idea about whether electron is going with clockwise spin or anti-clockwise spin. If the electron is going with clockwise spin, right, the value of S is taken as plus 1 by 2. And if the electron is going with anti-clockwise spin, the value of S is taken as minus 1. Just these are the two things which you need to remember. See, first of all, you know, electron, first of all, revolves around the nucleus. It revolves around the nucleus. At the same time, when the electron will be revolving, at the same time, electron will be spinning too. It will be spinning too, right? If it is a clockwise spin, S is plus 1 by 2. If it is anti-clockwise spin, S is equal to minus 1 by 2. These are the just two things which you have to remember. And spin angular momentum is given by the formula under root of S into S plus 1 h by 2 pi. Under root of S into S plus 1 h upon 2 pi. Okay? S represents here the sum of spin. Well, this is not required. Okay, this spin angular momentum is technically not in your syllabus. You just have to remember when S is plus 1 by 2, it means electron is going with clockwise spin. When S is minus 1 by 2, electron is going with anti-clockwise spin. That's all. Okay? Right? I hope all this is super clear to you. And if all this is super clear to you, then this table, I think, will summarize everything. For n is equal to 1. N is equal to 1 means first shell. In the first shell, there is only one subshell. For that subshell, L value is 0. That means that is S subshell, right? M value is also 0. M value 0 means there is only one orbital. And you call that orbital as S orbital. 2 minutes back only we discussed all this. If n is equal to 2, L can have 0 to n minus 1, 0 to 2 minus 1, so 0 and 1. N can have two values. Sorry, L can have two values, 0 and 1. 0 and 1. So in second shell, there are two subshells, S subshell and P subshell. In S subshell, there is one orbital. In P subshell, there are three orbitals. Perfect. Similarly, N is equal to 3, third shell. Third shell means three subshells, S subshell, P subshell, D subshell. S subshell has got one orbital, P subshell has got 3 orbitals, and D subshell has got 5 orbitals. Perfect. All this we discussed in detail. Now, people, comes a term that is shapes of orbitals. This is important. Okay. Only the shape of S orbitals, P orbitals, and D orbitals you have to understand and remember. First of all, if you talk about the s orbital, what is the shape of s orbital? If I ask you, s orbital is spherical in shape. S orbital is spherical in shape. How exactly it looks like? Let's say this is the nucleus, and this is your s orbital, which I'm showing you. This is basically a boundary surface diagram, which I'm showing. This is how your s orbital looks like. You should know it. Okay? Your s orbital, which is spherical. Which is spherical. If you talk about your p, if you talk about your p orbital, well, p orbitals can be, it can be px, it can be py, or it can be pz. First of all, let me tell you, your p orbitals are dumbbell shaped. Your p orbitals are dumbbell shaped, like this. Your p orbitals are dumbbell shaped. Now, px, py, pz, how do I show it? Have a look properly, what do I do? If I have to show px, see how exactly I'm going to show it. My dear students, let's say this is y-axis, let's say this is z-axis. So this plane over here is your yz plane. This plane over here is your yz plane. Therefore, x-axis would be perpendicular to this plane. This is your x-axis. This is your x-axis, right? In case of your px, the lobes, they lie along x-axis. In case of your px, the lobes, they lie along x-axis, like this. Lobes lie along x-axis. Okay? Lobes lie along x-axis. That means electron density, it lies along x-axis. Electron density lies along x-axis, right? Do you see this plane in the middle? Do you see any electron density on this plane? There is no electron density on the plane. I'll be calling this particular plane as nodal plane. Nodal plane. Which is my nodal plane? I'll say YZ plane over here in PX is my nodal plane, on which there is no electron density. On which there is no electron density. If I show you PY, how do I show you PY? See, let's say this is your, for example, z-axis. Let's say this is your x-axis. Therefore, perpendicular to this plane, there would be y-axis. There would be y-axis, right? Now, in case of py, the lobes will be along y-axis like this. This is one of the lobe. This is one more lobe. The lobes are along y-axis. Perfect. Do you see in the middle, there's a plane cutting this orbital. There's a plane cutting this orbital. On this plane, there is no electron density. And that plane on which there is no electron density, you call that as nodal plane. So which is my nodal plane here? It is the XZ nodal plane. It is the XZ nodal plane. Similarly, you can make PZ as well. In case of PZ, the nodal plane will be, the XY plane. Okay. So this is how your p orbitals look like. Similarly, when you talk about your d orbitals, first of all, your d orbitals, they are double dumbbell shaped. They are double dumbbell shaped. How many d orbitals do we have? We have discussed it. We have got 5 d orbitals. One is your dxy, one is your dyz, one is your dzx, one is your dx square minus y square, and one is your dz square. These are the 5 d orbitals which we have. Okay. Now, one by one, let's see how they look like. I told you your d orbitals, they look like double dumbbell shape. Okay. See, dxy. Understand. I hope I'm clear till here. See guys, if you talk about your dxy, let's say this is your x-axis. Let's say this is your y-axis. Okay. X-axis, y-axis. Perfect. In case of your dxy, the lobes lie between the axes. Lobes lie between the axes, or the lobes lie between the axes. Guys, have you studied coordination? In coordination, we have discussed all this. Or let me just make it simpler for you. If this is your x-axis, this is your y-axis. In case of dxy, the lobes, they lie between the axes like this. This is your dxy. This is your dxy. If I ask you how many nodal planes do you see? How many nodal planes do you see? See, I can draw one plane in the middle and there will be no electron density on this plane. I can draw one plane like this and there will be no electron density on that plane. So how many nodal planes are here? You have got two nodal planes. What would be the names of these two nodal planes? One is going to be your YZ nodal plane. One is going to be your XZ nodal plane. There are two nodal planes here. DYZ. 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 Let's say this is your y-axis, this is z-axis, right? DYZ. Y-axis, z-axis. Now again, lobes between the axes. Lobes between the axes. So how many nodal planes again? Two nodal planes. Again, there are two nodal planes, right? One of the nodal plane will be xy. One more nodal plane will be xz. These are the two nodal planes present in DYZ. If I talk about dzx, let's say this is z, this is x. This is your dzx. Perfect. Again, you have got two nodal planes here. And you can name them zy and xy. Okay. Now comes your dx square minus y square. Dx square minus y square. If you talk about your dx square minus y square, right? This is the d orbital, this x-axis, this y-axis. This is the d orbital in which the lobes, they lie along the axes. This is your x, this is your y. This is how your dx square minus y square looks like. Again, you have got one nodal plane, two nodal planes. There are two nodal planes present. One is going to be, there are two nodal planes present. One is going to be your YZ nodal plane. One is going to be your XZ nodal plane, right? And finally, when it comes to your DZ square, let's have a look on how DZ square looks like. If I talk about DZ square, see guys, let me show it to you properly. For example, this is your x-axis, this is the y-axis. So this plane is my xy plane. Okay, this is my xy plane. This is going to be your z-axis. This is going to be your z-axis, which is perpendicular to xy plane. Now your dz square, see, right now it looks like a p orbital, right? Right now it looks like a pz. But there is one more thing here. In pz, this xy plane is a nodal plane. But here on xy plane also, you'll find electron density like this. On xy plane also, you'll find electron density like this. Okay? So this is your electron density, this is electron density, as well as this is your electron density on xy plane as well. In case of what? In case of your dz square. Okay? And remember, in case of dz square, there are two conical nodal surfaces. In case of dz square, there are two conical nodal surfaces. There are two conical nodal surfaces. There are two conical nodal surfaces on which there will be no electron density. Are we clear till here? Are we clear till here, guys? This was your shapes of orbitals, how your orbitals look like. Now, my dear students, one of the most important topics from which question frequently comes, that is calculation of nodes. Calculation of nodes. What is a node, first of all? If I ask you, what is a node? Node is basically the region. It is the region around the nucleus. Node is basically region around the nucleus on which there'll be no electron density. I'll say node is basically the region where psi square is equal to 0. The region where there will be no electron density. The region where there will be no electron density. That's a node. That's a node. You'll understand this a bit more in detail in some time. Now, these nodes are actually of two types. These nodes are actually of two types. So one is called as radial, or you call it as the spherical node. You call it as the spherical node. One is going to be your angular node. One is going to be your angular node. Well, first of all, total number of nodes are given by the formula n minus 1. Angular nodes are given by the value of L. Radial or spherical nodes are given by the formula n minus L minus 1. N minus L minus 1. Now guys, you will understand all this in detail now. First of all, you need to remember total nodes, spherical nodes, angular nodes. Okay, total nodes. Basically, we have got spherical nodes, angular nodes. So, radial nodes plus angular nodes makes it total nodes. This plus this makes it total number of nodes. Okay. Now try to understand what do I say. Now try to understand what do I say. Try to understand what do I say. For example, I've got 1s orbital, 1s. Okay. I'm talking about 1s. In case of 1s, can you tell me what is the value of n? N value is 1. Okay. What is the value of L for S? 0. If I want to calculate total number of nodes, n minus 1. N minus 1. So there is no node in case of 1s. There are 0 nodes in case of 1s. 0 nodes. There is no node in case of 1s. Okay. My dear students, if you want to plot a curve between psi and r, if you want to plot a curve between psi and r, remember psi versus r as well as psi square versus r. Psi versus r as well as psi square versus r. In case of s orbitals, they start from the top. In case of S, they start from the top. They start from the top. Okay. So, they start from the top, for example, from here. But this curve is not going to touch the r-axis. This curve is not going to touch the r-axis. Because if this curve touches the r-axis, at that point, there will be a node. That point would represent a node, but there is no node in case of 1s. So it's not going to touch here. Okay. Is any part of this graph down the r-axis? No. If there was any part of this graph down the r-axis, you were supposed to rub that and take its reflection, which I'll show you in some time. So there is no portion of this graph down the r-axis. So make psi square versus r as such. So this is your psi square versus r for 1s. Okay, this is your psi square versus r for 1s. Now, if I talk about 2s, from 2s you'll understand properly what exactly I'm saying. These are your probability distribution curves. In case of your 2s, my dear students, in case of your 2s, what is the value of n? N value is 2. What is the value of L for s? L for s is 0. Total number of nodes will be equal to n minus 1. So 2 minus 1 is 1. Angular nodes is equal to the value of L. L value is 0. Our spherical nodes will be n minus L minus 1. That's equal to 1. Okay. Now you can show them over here as well. This is psi versus r. This is psi square versus r. And in case of S, all the graphs, they start from the top. They start from the top. There is one node. There is one node. So that means when the graph will start from the top, it will come down. It will touch the r-axis once. It's going to be like this. It's going to touch the r-axis once. Okay. And this particular point represents this radial node, spherical node, I mean. Okay. This point represents your node. Now, if you want to plot psi square versus r, do you see any part of the graph down the r-axis? Yes, this part of the graph is down the r-axis. So just erase this and take its reflection over here. So how do I get it? From here to here, it's the same. Now this particular portion we have to erase and we have to take its reflection from the top. Okay, this is your psi square versus r in case of 2s. Perfect. Similarly, my dear students, if you have got, for example, 3s, you can do the similar procedure for 3s as well. I believe you can do that. If you have got 3s, in case of 3s, what is the value of n? N value is 3. What is the value of s? S value is 0. Sorry, what is the value of l? L value is 0. How many total nodes are there? N minus 1. So 3 minus 1 is 2. How many angular nodes are there? How many angular nodes are there? Value of L. L value is 0. How many spherical nodes are there? N minus L minus 1. The value comes out to be 1. Okay. Now, you can plot these two graphs easily. One is your psi versus r. One is your psi square versus r. One is your psi versus r and one is your psi square versus r. My dear students, since we are talking about S, in case of S, all the graphs, they start from the top. Okay. How many nodes are there in total? 2. Start from the top, first node, second node, and we are done. Right? Is there any portion of the graph down the r-axis? Yes, this portion. This portion. So erase this and take its reflection. So the psi square versus r will be like this. Okay. So this is for 3s. This is for 3s. Okay. Am I clear? Am I clear, guys? Now, similarly, we are going to see for P as well. We are starting with 2P. We are starting with 2P. Okay, we are starting with 2P. We are starting with 2P. First of all, in case of 2P, but I think we should not study P because P is not in your syllabus. In your syllabus, it's clearly mentioned psi and psi square for 1s and 2s. So P, let's not discuss. It's a wastage of time. So is it clear till here? Is it clear till here, guys? Tell me in the chats quickly. Is everything clear till here? I want to know. Is everything clear till here? I want to know. Can you tell me the answer of this question? See, frequently you get these sort of questions. N, L, M, and S. You have to tell me the incorrect combination. You have to tell me the incorrect combination. Let's say this is 5, this is 4, this is 3, and this is plus 1 by 2. Second, 5, 5 plus 4 and plus 1 by 2. Tell me which one is the incorrect set of quantum numbers. 4, 3, 4, 3, minus 4, minus 1 by 2. 4, 3, 2, 0. 6, 5, minus 5, plus 1 by 2. Tell me the incorrect set of the contour numbers. What are the incorrect set of the contour numbers here? See, L is from 0 to n minus 1. M is from minus L to plus L. S can have two values, either plus 1 by 2 or minus 1 by 2. If this is 5, this will be from 0 to 5 minus 1, 0 to 4. This is correct. M, minus L to plus L. L is 4, so minus 4 to plus 4. Minus 4 to plus 4. 3 comes in between. Yes. S plus 1 by 2. So first one is correct. Second, if n is 5, L has to be from 0 to n minus 1. 0 to 5 minus 1. 0 to 4. 5 is not possible. So this is incorrect set. See, L here is 3. M is minus 4. But we know M is from minus L to plus L. So it can be minus 3 to plus 3. Minus 4 cannot be possible here. This is the correct set, incorrect set. 4, 3, 2. S can have only plus 1 by 2 minus 1 by 2. It cannot be 0. So this is incorrect set. 6, 5, minus 5 plus 1 by 2. This is correct set. I hope this is clear. I hope this is clear. Yeah? All this is clear? All this is clear? Sir, previous slide. This is the previous slide. All right, tell me one more question. I'm giving you one more question. Tell me the answer of this one. Can you tell me if I plot a graph between psi square versus r? Okay, the graph is like this. Can you tell me for which s orbital this is? For which s orbital this is? Is it for 3s? Is it for 4s? Is it for 5s? Is it for 6s? For which s orbital this graph is valid for? See guys, first of all, it's S because the graph is started from the top. So this is your node, second node, third node. So there are in total 3 nodes. Total number of nodes is given by the formula n minus 1. And total nodes here are 3. So n minus 1 is 3. That means n value is 4. If n is 4, so it has to be for 4s. Be careful with this. It has to be for 4s. Okay. Similarly, for example, if I give you a question like this. Let's say I'm plotting a graph between psi versus r. Psi versus r. Let's say the graph is like this. Okay, I'm telling you this is for S. For which S this is valid? For which S? See, node, second node, third, fourth, fifth. There are 5 nodes. So n minus 1. Total nodes is equal to 5. So n here is 6. So this will be your 6s. This would be your 6s, right? Correct? I believe all of this is clear. Now, my dear students, there is one topic left, that is electronic configuration. How do you write electronic configuration? My dear students, in order to write electronic configuration, 3 rules are to be taken into consideration. Okay, this is the last topic of the session. In order to write the electronic configuration, we are done with 101 slides by the way. We are done with 101 slides and there are few more to be done. Yeah, that's it, few more. Few more. In order to write the electronic configuration, we have to consider 3 rules. One is called as Bohr's principle, Hund's rule, Pauli's exclusion principle. Bohr's principle, Hund's rule, Pauli's exclusion principle. What Bohr's rule says? Bohr is a German word, first of all. Bohr is a German word which means build up. Bohr is a German word which means build up. Okay? As per Bohr's rule is concerned, we are going to fill the electrons in the orbitals. We are going to fill the electrons in the orbitals as per their increasing order of the energies. That means that orbital which has got lesser energy will be filled first. That orbital which has got lesser energy will be filled first. According to this principle, filling of electrons in different orbitals is done in increasing order of the energies. Lowest energy orbitals will be filled first. Now the point is, how do we get to know which orbital is having lower energy and which orbital is having higher energy? For that, there is a rule. There is a rule which is called as Bohr-Bury's rule. Which is called as Bohr-Bury's rule. And let me tell you this particular rule, right, which is the Bohr-Bury's rule, or you call it as the N plus L rule. N plus L rule. What is N and what is L? N is principal quantum number, L is azimuthal quantum number. My dear students, remember just one thing. That orbital whose N plus L value is less, that orbital whose N plus L value is less, will have lesser energy. Will have lesser energy. And similarly, that orbital whose N plus L is more, will have more energy. Will have more energy. And remember, in case, if N plus L value for two orbitals comes out to be same, if N plus L value for two orbitals is same, then that orbital having lesser value of N will have lesser energy. That orbital whose N value is less will have lesser energy, right? Remember this particular stuff as well. Now, for example, you have got 1s, you have got 2s, you have got 2p, you have got 3s, you have got 3p, you have got 3d, you have got 4s. Let me write till here only. If I ask you what is the N value for this, N is 1. What is L value for S? That is 0. So N plus L here is 1 plus 1, 1 plus 0 is 1. N value here is 2, L value is 0, N plus L is 2. N value here is 2, L value is equal to 1, N plus L is 3. N value here is 3, L value is equal to 0, 3 plus 0 is 3. N value here is 3, L value here is 1, so 3 plus 1 is 4. N value here is 3, L value for D is 2, 3 plus 2 is 5. Similarly, N value is 4, L value is 0, N plus L is 4. That orbital which has got lesser N plus L has got lesser energy. So 1s has got lesser energy, followed by 2s. Now 2p and 3s, they have got same N plus L. Now decide on the base of N. The one that has got lesser N will have lesser energy. So 2p has got lesser energy than 3s, right? Now 3p and 4s, they have got same N plus L. Decide on the base of N. So 3p has got lesser energy. Then comes your 4s, and at the end, it's going to be 3d. So this is the energy order. This is the energy order of these orbitals. So electrons are to be filled in these orbitals as per the same energy order. So basically 1s has to be filled first, then 2s, then 2p, 3s, 3p, 4s, 3d. Okay? Right? And remember, this order, this N plus L rule, this Bohr-Bury's rule, it is valid for multi-electron system. It is valid for multi-electron system. In case of single electron species, for single electron species, like hydrogen, N plus L rule is not valid. N plus L rule is not valid for hydrogen. In case of hydrogen, let me tell you, 1s has got lesser energy, 2s and 2p, they have got equal energy, 3s, 3p, 3d have got equal energy, 4s, 4p and 4d have got, and 4f have got equal energy. This particular energy order is valid for the single electron system. Okay, this is valid for the single electron system. Do remember this stuff as well. Sir, in my Aadhaar card, my father's name is not same like my 10th certificate, but in my first attempt, I haven't faced a problem. So let me know, is it required to change? It is better if you change your Aadhaar card details. You make your Aadhaar card details as per your 10th mark sheet. Okay, do that. Do that tomorrow only. Because Aadhaar card updation, it can happen in 2 days also. It might take a week. It might take 20 days also. Okay? It's better you change it. Better you change it. Okay? So guys, this was your Abbas rule. I hope this is clear. I hope this is clear. Now, do you know what are degenerate orbitals? You would have heard about degenerate orbitals. What are degenerate orbitals? Degenerate orbitals are basically the orbitals of same subshell which have got equal energies. For example, you have got p subshell. P subshell has got 3 orbitals, your px, py, pz. So these are the 3 orbitals of p subshell which have got same energies. I'll be calling them as degenerate orbitals. D subshell has got 5 d orbitals. They have got same energy in absence of the field, in absence of any field. Okay, so I'll be calling them again as the degenerate orbitals. So degenerate orbitals, if you do not know, these are the orbitals belonging to the same subshell, right, which have got same energies. You call these orbitals as the degenerate orbitals. Now guys, there is one more rule which you need to know before writing the electronic configuration. What is that rule? That is your Pauli's exclusion principle. Pauli's exclusion principle simply tells us one thing. No two electrons in an atom can have same set of all the 4 quantum numbers. If you select 2 electrons in an atom, all the 4 quantum numbers won't be same. At least there will be 1 quantum number different. Okay? No 2 electrons in an atom will have the same set of 4 quantum numbers. Okay? Perfect. And at the same time, remember one more thing. An orbital, it can accommodate maximum of 2 electrons. And that too, those 2 electrons should be having the opposite spin. This is one more rule which you need to know before writing the electronic configuration. Okay? Perfect, people till here? So according to this particular principle, no 2 electrons in an atom can have same set of 4 quantum numbers. Minimum there will be 1 quantum number different. Or I can say, an orbital can accommodate maximum of 2 electrons, and those 2 electrons will be having the opposite spin. You'll see its application in some time. Okay? You'll see its application in some time. Can you tell me the answer of this question? Can you tell me the answer of this question? How many maximum electrons can be accommodated in 3D orbital? Read the question carefully. Read the question carefully. How many maximum electrons can be accommodated in 3D orbital? Do not say 10. Okay? It's mentioned as 3D orbital. See, normally what people think, they think they have asked 3D subshell. And in case of 3D subshell, there are 5D orbitals. There are 5D orbitals. And you know, every D orbital accommodates maximum of 2 electrons. Right? So normally people say their answer is 10. Perfect. But if you think logically, it is 3D orbital. They are talking about one of the orbitals of 3D. And one of the orbitals of 3D can accommodate maximum of 2 electrons, that too with opposite spin. That too with opposite spin. Okay? Perfect. So it's not 10 electrons, it is 2 electrons. Now similarly, when you talk about Hund's rule, Hund's rule simply says that in case of degenerate orbitals, pairing won't happen unless each degenerate orbital gets 1 electron each. That too with the same spin. For example, let's say I have to write P3 configuration. In case of P subshell, there are 3 p orbitals. One is px, py, pz. Okay? One is px, py, pz. One of the ways of writing P3 configuration is 1, 2, and 3. One more way, 1, 2, and 3. As per Hund's rule, this is the correct way of writing. See, these are the 3 degenerate orbitals in case of p subshell. In case of p subshell, these are its 3 degenerate orbitals. In case of degenerate orbitals, pairing won't happen. Pairing won't happen unless each degenerate orbital gets one electron with the same spin. Okay? For example, you have got d6 configuration. D6 configuration. How many d orbitals are there? There are 5 d orbitals. So, first electron will go here, second here, third here, fourth here, fifth here. Now pairing will start. Now pairing will start. Right? So, remember, pairing in degenerate orbitals won't happen unless each degenerate orbital gets one electron, that too with the same spin. Okay? Now, my dear students, you can easily write the electronic configuration. First of all, 1s has to be filled, lesser energy, 2s, 2p, 3s, 3p, 3d, 4s. Okay? 1s has got, s has got 1 orbital, s has got 1 orbital, p has got 3 orbitals, right? This s has got 1 orbital, this p has got 3 orbitals, this d has got 1 orbital, and this d has got 5 orbitals, and s has got 1 orbital. Perfect. Now easily you can write the electronic configurations. For example, hydrogen, helium, you know all. Let's say I need to write the electronic configuration of magnesium. For example, magnesium. Its atomic number is 12. So there are 12 electrons. So 1, 2, 3, 4. Degenerate. 5, 6, 7, 8, 9, 10, 11, 12. This is its configuration. So it's going to be 1s2, 2s2, 2p6, 3s2. Okay. For example, I have to write the electronic configuration for, let's say, sulfur, whose atomic number is 16. Sulfur, whose atomic number is 16. Okay. Atomic number is 16. So till here we have filled 12, right? 12 are filled till here. 13, 14, 15, 16. That's it. Okay. So its configuration is going to be 1s2, 2s2, 2p6, 3s2, and 3p, 3p4. This is something which you know from class 10th as well. There are just 2 things which you have to remember here. One is the electronic configuration of chromium. One is the electronic configuration of copper. Just remember it directly. My dear students, the expected electronic configuration. The expected electronic configuration of chromium is 3d4, 4s2. This is the expected electronic configuration of chromium. Chromium whose atomic number is 24. This is expected. See, we have filled 16 till here, 17, 18, 19, 20, 21, 22, 23, 24. What did I do? I think I have mentioned it wrong. This is 4s first. Yeah, 4s, then your 3d. So I have to mention it over here. First is 4s as per n plus n plus l, then comes your 3d. All right, now it's clear. See, how many we have filled here? 2, 4, 4 plus 6 is 10, 10 plus 2 is 12, 12 plus 6 is 18, 19, 20, 21, 22, 23, 24. So the outermost configuration of chromium should be 3d4 and 4s2. This is expected. This is expected. But in case of chromium, 4s and 3d, they have got almost similar energies. 4s and 3d, they have got almost similar energy. So one of the electron from 4s shifts here. So its actual configuration becomes 3d5, 4s1. Why this shifting takes place? Because when the shifting takes place, what do you get here? You get 3d5. You get half-filled configuration. You get half-filled configuration. Okay? And half-filled configurations are more stable. Half-filled configurations are more stable than partially filled configuration. That is the reason why this is the actual configuration of chromium. Okay. Same goes for copper. Copper, its expected configuration is what? 3d9 4s2. This is its expected configuration. But if you talk about its actual configuration, it is 3d10 4s1. One of the electron shifts here, right? When the electron shifts here, it gets fully filled configuration. And fully filled configurations are more stable than partially filled. So this is your actual configuration of copper. Perfect. So remember one simple thing. Fully filled configurations are more stable than your half-filled configurations, which are more stable than that of partially filled configuration. Partially filled configurations. Now you must be thinking why full half-filled configurations are more stable. There are two reasons for it. Just remember them as such. One is exchange energy. In case of half-filled configurations, there is more exchange energy. Okay. Or you can say another reason is symmetrical distribution of electrons. Or you can directly say symmetry, because you always say symmetry leads to stability. Okay. Perfect. Remember these two reasons directly. Half-filled configurations are more stable because of exchange energy, or you can say because of more exchange possible, or you can say because of symmetry. Perfect. Right? Now guys, one more thing. How do you calculate the magnetic moment? Magnetic moment is calculated by the formula under root of n into n plus 2 Bohr magnetrons. Okay. And this n, what does it represent? It represents the number of unpaired electrons. Okay. Magnetic moment, which I represent with mu. Is equal to under root of n into n plus 2 Bohr magnetron. Okay. Remember, if mu is non-zero, we call the species as paramagnetic. If mu is 0, we call the species as diamagnetic. If mu is non-zero, we call the species to be paramagnetic. If mu is equal to 0, we call the species to be diamagnetic. Questions can be asked from this particular point as well. Okay? Questions can be asked from this particular point as well. Like this. Calculate magnetic moment of the following species. For example, you have got Fe dye positive. If you talk about the Fe dye positive, right? What is the outermost configuration of iron in general? It is 3d6 4s2. But do you see Fe dye positive? Dye positive means you need to take 2 electrons out. So it becomes 3d6 configuration. How this 3d6 configuration looks like? It's going to be 1, 2, 3, 4, 5, and 6. How many unpaired electrons do you see here? 4 unpaired electrons. N value is 4. If n value is 4, you can calculate magnetic moment under root of n into n plus 2. So 4 into 4 plus 2. So 4 plus 2 is 6. 6 4 is 24. Root of 24 is 4.92 Bohr magnetrons. Perfect. So like this, you can easily solve these sort of questions. Thank you, HSP Baba. Thank you. Perfect. Similarly, you can take any of the examples and I believe you can easily solve it. Yeah? Perfect. We are about to finish the session in like 2-3 minutes. That's it. Okay, can you let me know the answer of this question? Which of the following has got a maximum number of unpaired electrons? Maximum number of unpaired electrons. Maximum number of unpaired electrons. You need to solve this. And you need to tell me its answer. Which of the following has got a maximum number of unpaired electrons? Unpaired electrons. How come it's going to be magnesium? Magnesium dye positive won't have unpaired electrons. Unpaired electrons, guys, unpaired. Magnesium has got 1s2, 2s2, 2p6, 3s2. But this magnesium dye positive. So take these 2 electrons out. So there's no unpaired electron here. Why you are saying magnesium? It's going to be iron dye positive. 3d6 4s2. Take 2 electrons out. So it's 3d6. It has got 3d6 configuration. So there'll be 4 unpaired electrons, which would be maximum on all. Which would be maximum on all. Tell me the answer of this question. I told you right now. In case of chromium, the actual configuration is 3d5 4s1. Right? This is the question which has been asked. Okay? Perfect. The diagram in which a Bohr's principle is violated. A Bohr's principle says that the lower energy orbitals should be filled first. Do you see the second case? Lower energy orbital is not filled first. There's only one electron here. Then they have filled this. So here your Bohr's principle is violated. Here your Bohr's principle is violated. Right? The first 2 electrons should have been in this orbital. They are not. Bohr's principle is violated here. Okay. Tell me the answer of this question. Any p orbital can accommodate maximum of? Quick. Any p orbital can accommodate maximum of 6 electrons. A lot of people will say 6 electrons. It is p orbital, it's not p subshell. So 2 electrons with opposite spin. Okay, be careful with all this. Arrange them on the basis of their decreasing energy. So n plus L rule. For 5, n is 5, L is 3. 5 plus 3 is 8. N is 6, P is 1. 6 plus 1 is 7. 5 plus 1 is 6. 4 plus 2 is 6. So maximum 5F followed by 6P. Among these two, 5P will have more because n value is more here. So it has to be A only. A is the correct answer. N plus L rule, guys, nothing else. N plus L rule, nothing else. The total number of atomic orbitals in the 4th shell. Number of atomic orbitals in a shell is equal to n square. Okay? Maximum number of orbitals in a shell is equal to n square. So 4 ka square, are they asking about 4? Yes. 4 ka square is 16. So 16 orbitals. Got it? Of course, these sort of questions only come in your exam. The orbitals are called degenerate when their energy is same. Okay? Nothing. An ion has got 18 electrons in its outermost shell. Which ion it's going to be? Which ion it is going to be? 18 electrons in its outermost shell. Okay? Chalo, this is your homework question. And you can easily solve it, I'm sure. And with this, we are done with our, oh my God, why? Why did I show you the answer? Cu positive. Check in the 3rd shell. In the last shell, there are 10 plus 6, 16 plus 2, 18. 18 electrons in the last shell. Anyways, okay, Cu positive. It just happened, guys. Okay, so with this, our first chapter of this series is done and dusted. Now do one thing. You can take any of the modules, any of the coaching material. Try solving that tomorrow. I'm sure you are going to solve majority of the questions of that module. Yeah? And do let me know in the comment section of this particular video about this particular series and this particular session. Okay? I'll check your comments one by one. Perfect? Chalo, I'm taking a leave with this. Our next session is going to be, you know it already, that is your general organic chemistry. Take care, God bless you all, and